My pleasure. Uh, okay, so I will also, again, because I'm trying to sort of say things about uh, maximum nullities. We also, at one point in 2005, with Barioli and Hogben, we looked at, why do you stress so much about a positive semi-definite thing with SAP or a generalized Laplacian with SAP? Why don't you just look at S of G with SAP? And we designated that maximum nullity like this, and we wrote down a bunch of cool theorems. I suppose. I mean, I'm a bit biased, obviously, but I want to draw your attention to bullet number 4, which was not done by me. This was Hogben and Hein van der Hulst, where they actually used this parameter xz to characterize the graphs with maximum nullity 2. So you remember the graphs with maximum nullity 1 was a path. What are the graphs with maximum nullity 2? And I'll say here, I say there are basically linear two trees. Uh, of course, there are other graphs that are not linear two trees that have this parameter, that satisfy this equation, but there's only a finite number of exceptions, and I'm not going to go through it. But this parameter, even though it sort of was born out of just trying to unify things, it actually became very useful in trying to sort out capital M equals 2. So I mean that's nice. Um, okay, so looking forward towards MQ. Let me tell you a little bit about a sort of a coloring game on graphs that's known as zero forcing. It was originally conceived in 2006, but the concept, of course, was derived in other situations as well. So the idea of zero forcing on a graph is you start with a graph. You're allowed to fill in all the vertices are unfilled, if you will, and then you're allowed to fill in vertices, and then you can invoke this sort of filling rule. And the idea is you can fill a vertex for a cost of a token, and then at no cost you can apply this filling rule, which I'll tell you about in a minute. And the filling rule is up here. If a filled vertex has a unique unfilled neighbor, then the rule is that unfilled neighbor becomes filled. So the game is the following: you have a graph, you're allowed to spend some tokens, and then you can apply this filling rule as much as possible. And then your hope is you can actually fill the whole graph. And if you're able to fill the whole graph, that's known as a zero forcing set. And then you want to know what's the fewest number of tokens I need to spend in order to fill the graph. And that's called Z of G. Again, we refer to it as the zero forcing number, but I mean, in people who do graph searching, this was also known as the fast mix search number, just for interest's sake. So it was derived independently of this fast mix search stuff, but turns out to be similar. And again, I say there's all these other situations where it was derived. Okay, so remember, one of my goals was to look at this parameter MQ, and the MQ, it turns out, can be bounded by, again, another kind of zero forcing, but you have to be a little bit more cautious. You have to introduce a second player, and then you have a much more sort of complicated filling rule, which again, I don't want to spend too much time going through as my time is limited. But the point is, there is this game. It's now a two-player game as opposed to just a one-player deterministic game. And again, here's a tree where the zero forcing number is 4. Here's some filled vertices that'll you can use to fill up, and then the Z1 number. So here, where you have Q equal to 1, it turns out that is actually 3. I'm not going to do the game here, but the point is that you have now these ZQ numbers, and they are actually non-decreasing. And the maximum overall Q turns out to be the zero forcing number that we started with. So that guy's on top. And so the point is, okay, so where am I going with all this? Well, these folks actually proved that this zero forcing numbers, which is just a purely combinatorial game you can play, bounds the MQ. Okay, so you get this sort of nice upper bound, combinatorial upper bound on all these maximum nullity parameters. Okay. And now what's happening is now people are starting to say, like, when does equality hold? When are there gaps? If there are gaps, how big can the gaps be? There's lots of questions that can be asked. And I'll just remark here that these gentlemen, this is how they came up with this. They basically focused on this isotropic subspace given by this equation here, and then just sort of worked out what was going on. But this was a beautiful result done by these guys. So okay, so you then have this upper bound, and you want to know when is it possible that equality holds. And maybe I should just step back for a second. Remember, for trees, okay, so for trees, I understand I've gone fast, but for trees, this number was known. Remember, it's the maximum disconnection number minus Q for any tree. But I'll say here, and I'm confident in saying, ZQ of a tree is extremely complicated. And in fact, there is no characterization for ZQ of a tree. Very complicated. But MQ is very easy for trees. So this is somewhat unusual. The algebraic parameter is straightforward, but the combinatorial parameter is just off the wall. However, for threshold graphs, here's some existing work on threshold graphs. So people were worried about these nullities. And then, so you see here, this is M0, and this is the maximum, right? And then what we were able to show as part of the discrete math research group is we were actually able to show that equality holds for threshold graphs. Don't stress out too much about what this is. This is known as the creation sequence of a threshold graph. And you can show that these two parameters are equal for every Q. And in fact, they equal this number, where capital A is defined in terms of that little a is defined in terms of that creation sequence. So this is just a class of graphs where we can actually compute both parameters. We verify both parameters are the same, and we can write down a formula. So, that's rewarding and gratifying that at least we have some, mildly complicated families of graphs where we know how to compute these things. Although I respect the fact that threshold graphs are very structured. So let me just close by looking at the inertia set of a graph. So remember, I've moved along by saying I want to focus in on the number of negative eigenvalues. And so if you start going down that road, then it's very natural to look at the inertia of a symmetric matrix. So the inertia is a triple where you look at the number of positive eigenvalues, the number of negative eigenvalues, and then, of course, the number of zero eigenvalues or nullity. But because these three numbers have to add to the size of the matrix, I may as well only consider two. And then I get the third, for free. And so this has now been loosely referred to as the partial inertia, although it's enough to describe everything. And so I talked about the inverse eigenvalue problem at the beginning of this presentation. There's also the inverse inertia problem, which is, of course, hopefully in some sense a little bit easier. Whereas instead of specifying all the eigenvalues, I just tell you how many are positive and how many are negative. Can I sort of realize that partial inertia? And this is also not completely resolved, but I mean, it's been resolved in many situations. And I just write one example down here regarding a path. So this is the path Pn. But okay, so very recently, I was doing some work where I looked at the hypercube. Now, the hypercube is it's a fascinating graph for many reasons, and I'll just note here that, of course, a lot's been known about the hypercube, and in fact, the M0 equals M equals ZQ equals half the number of vertices, 2 to the d minus 1. So those numbers are all known, and so then we started working. I started working this past year with Jeffy and Lin from Taiwan, and we wanted to focus in on what do the matrices look like that have this largest nullity, right? What do they look like? And it turns out that if you fix a matrix in S of a hypercube and you ask that its nullity be the largest possible, which is half the number of vertices, then it turns out you're only allowed to have these three possible inertias. So here's the nullity is 2 to the d minus 1. Remember, so the last coordinate was the nullity. this is the number of positive, and this is the number of negative. And so these are the only three possible inertias. This was a surprise to us. And what we were able to deduce here is that if you take, say, the hypercube Q3, which is just a conventional cube on 8 vertices, and you ask that you have a matrix with nullity 4, which is the maximum possible, half the number of vertices, then the inertia must have this form. So I'm simply repeating what I wrote above. But what I want you to notice is that if the inertia of the matrix is one of these three, then A cannot be an S1. I can't have exactly one negative eigenvalue, right? I mean, I have to have I have to have four negative eigenvalues, right? Probably this one is backwards. I probably have to be careful here, but you can have 2 or 4 negative eigenvalues. And furthermore, you can even work harder if you want, and show that this list is realizable. I'm not saying this is an inertia list. This is a multiplicity list now, but this one is not. And basically, this one is not realizable because of this theorem up here. And so I bring up these two consequences as a way to close my presentation, because in fact, these two consequences actually resolve some outstanding conjectures on the inverse eigenvalue problem. So these were two questions that were asked or have been asked. And you'll remember for a path, I made a comment that M0 and M1 of the path are ordered, right? And it was asked in general, is it the case that M0 is at most M1? And the second question was a much broader question about multiplicity lists. And if two multiplicity lists have a certain majorization relationship, and you know that the larger one is realizable, is the smaller one realizable in the majorization order? These were two posed questions that were open, and the results I wrote on the previous slide actually disprove both of them. So it turns out that for the hypercube, M1 is strictly less than M0, which is 4. And it turns out that this list actually majorizes this list. And so we actually sort of disproved that we resolved the other question in the negative as well. So that was, starting with this inverse inertia theory, you sort of go in and you're able to answer questions about the inverse eigenvalue problem for graphs. Okay, that will bring me to the end of my slide. There was lots of, sort of references here. And again, I'm happy to, if people want to email me, ask me more questions. I apologize I can't be there in person, but I'm very happy to sort of, answer any questions you have. Again, I have to sincerely thank Prasad for making this happen, and putting up with my patience, putting up with me not being there. And I thank you all for your attention. I appreciate you taking the time to listen. Thank you very much.
Any questions from the audience?
Professor, just I have one.
Not sure. It seems to be. Is it me or no?
You have to on.
No,
it's on.
You can still hear me?
Can I ask?
Yes.
Of course.
See, the Porter-Wiener theorem that you showed for nullity, does it readily follows from the classical Porter-Wiener theorem? Because multiplicity of 0 is the nullity, right?
Yes.
So your theorem follows immediately from the original Porter-Wiener theorem.
Which theorem does? Sorry.
The theorem that you showed, you proved, your theorem for nullity, which is a reminiscence of Porter-Wiener theorem that you told in your talk.
Okay, I didn't quite catch what you meant, but I mean, with regard to nullity of a tree, I mean, it's very possible that it follows from the Porter-Wiener theorem. I'm just not sure which one you're referring to. I
Yes, yes,
can.
yeah. Yeah, whatever you are telling here, that's what you, the slide that you showed, your theorem on nullity, the same analog of Porter-Wiener theorem.
Okay, so nullity of trees
Nullity of trees, yes, yes.
here.
No, no, before.
Oh,
I
excuse me.
think
Excuse me.
before 15th slide or like.
Oh, okay. Sorry.
Yes, this one, 15th. Yes,
Yes.
yes. Yeah, this one, does it follow immediately from the Porter-Wiener theorem? Or?
So
No,
the
no, okay.
yeah, it doesn't. Okay, so I see where you're going with this. I mean, it doesn't. Okay, it's very analogous to the Porter-Wiener theory, but it doesn't follow precisely from the Porter-Wiener theory, because the Porter-Wiener theory says that there's at least three branches that contain the nullity, right? And
Yeah.
so we were able to push it a little further when we have this restriction being in S1. But I I agree with you that we make strong use of the Porter-Wiener theory in this theorem.
Oh,
But it's a tad more general. But I mean that's maybe saying a bit more than it's worth. But you're absolutely correct, sir, that this is very much relies on the Porter-Wiener theory. Yes.
okay, thank you.
Yeah, of course.
Any other questions?
So sorry for missing the introduction about the speaker. So from the organizing team, I am saying sorry to you. Before thanking the speaker, I want to just say about 2 lines about the speaker. Sean Fuller is a professor in the Department of Mathematics and Statistics at the University of Rennes, where he is a leading member of the Discrete Mathematics Research Group with research interests in matrix theory, combinatorial matrix analysis, discrete mathematics, and algebraic graph theory. He earned his PhD in applied mathematics from College of William and Mary in 1999, and has since developed a strong international research profile, including work on total positivity and spectral properties of matrices and graphs, as well as co-authoring the book Totally Non-Negative Matrices. His scholarly contribution continues to influence the fields of matrix theory and graph theory, making him a respected figure in the international mathematics community. So thanks for your valuable talk. Sorry for changing the tradition.
No, this is the better way to do it. This is good. Yeah.
Thank you.
Yeah. So thanks the speaker.
Thank you very much.
So our next speaker is Professor Bozan Mahar.
Thanks, Prasad.
Yeah, sure.
I don't okay, Shanjan later. So I have this, right? I will use them. Yeah, kind of. The clicker.
Yeah, it's so you need not press this. You don't press this. This is forward and this is backward.
Okay, and is there a
Pointer it will not display. It is a white screen.
okay, so just forward backward.
Yeah.
And anything else? No, I will just reproduce it. It's not working, so
Sure. But the mic has to switch on. Which one? This one? Yeah, we have to switch on.
So I would like to introduce the next speaker. Professor Bozan Mahar is an internationally acclaimed mathematician. University, Canada, and has also been associated with the University of Ljubljana and the Institute of Mathematics, Physics and Mechanics, Slovenia. His research spans graph embeddings on surfaces, spectral graph theory, graph coloring, graph minors, and algorithmic aspects of graphs. One of his notable works is Graphs on Surfaces, co-authored with Carsten Thompson, is considered as a foundational reference in topological graph theory, and he has served in prominent editorial roles, including as editor-in-chief of the Journal of Combinatorial Theory, Series B. So with these few words, I welcome Professor Bhojan Mahar to take care of the session.
Okay, thank you. Can you get the clicker working? Yes, yes, it's right. Is forward. Okay. Okay. So thank you, the organizers, for this kind invitation to get me here. It's my pleasure to speak about the work. Maybe I hopefully will be interested to at least some of you, as I'm working mainly in graph theory, so it's not so much in matrix analysis. I will try to go slowly, and I'm presenting a theme which is which may be new to most of you because it concerns directed graphs. So it's the title. First, let me just present the co-workers. Saeed Akbari spent a year at Simon Fraser, and these results were obtained while he was visiting us. And Johnny Aloni and Stephen Shia, these are the USRI students, so two undergraduate students who collaborated with us, and Max is my postdoc. So what can one say about spectrally symmetric matrices related to graphs? So if you have a graph, then this is a well-known result that spectrum of the graph, so the eigenvalues of the adjacency matrix, is symmetric if and only if the graph is bipartite. So one way is easy, the other way is just a simple consequence of Perron-Frobenius theorem. So that's the very, very simple but interesting observation that you can get combinatorial property out of the eigenvalues. Now, a proof you can do also using the trace equalities. And let me just mention that if you take the adjacency matrix and you take the powers of the adjacency matrix, the diagonal entries have the information on the number of closed walks through particular vertices. So they count closed walks of length k in a graph. So that's the main correspondence to from matrices or powers of matrices to combinatorial properties of graphs. And of course, this relates to the spectrum because it's obvious that the spectrum is symmetric with respect to zero, if and only if all these odd trace moments are equal to zero. So that's the end of the story for undirected graphs. And the next thing I'd like to mention is about how to extend this to directed graphs. So I've been trying to motivate some research in algebraic graph theory on digraphs. Years ago, I introduced, together with my at that time PhD student Chris Terguo, we introduced the Hermitian adjacency matrix to a digraph. So if you just do the 0-1 adjacency matrix of a digraph, it's non-symmetric, and you lose the power of linear algebra. Of course, you still get Perron-Frobenius, but you lose the power of other properties. Now, but if you instead do the follow, you take the Hermitian matrix containing some complex entries, then you can keep the power of being like symmetric, so being Hermitian matrix. So here, in principle, you could take any complex number of of norm 1. So and you can just say that the entry in the matrix H, which I will use H instead of A for the adjacency, this Hermitian adjacency matrix, the UV entry is either this complex number, omega, or, and this is when the edge goes from, let's say, if the edge goes from 1 to 2, you put the, well, let me do it goes from 3 to 1, you put in the 3, 1 position, you put the value of omega. And if in the symmetric position, you put the complex conjugate, omega bar. So that's the rule. As I mentioned with my student Crystal Guo, we used the complex unity I as the first approach, and this was actually gave some quite nice results. But later on, I realized that there is a much more natural choice for this root of unity, namely taking the 6th root of unity. So this is a very particular root of unity that you take, but I will use the symbol omega throughout my talk, and you can then just assign this Hermitian adjacency matrix to every directed graph. So here I have on purpose, although I will not speak about directed graphs with multiple edges, but I have on purpose added the cases where you have multiple directed edges or edges in the opposite direction. So when you have more edges, you just sum up the contributions of these omegas or omega bars, right? So if you have the like between 1 and 2, you have both directed edges in both directions. Then you get omega and plus omega bar as the entry in the Hermitian matrix. And between 3 and 4, you get 2 omega or 2 omega bar, depending on which side you're looking at. So that's the this is the definition. It's just replacing 0 ones with 0 omega bars, and that's the Hermitian adjacency matrix. Well, I'd like to mention why this 6th root of unity, why I think that the 6th root of unity is the right one. Of course, the basic condition that omega times omega bar is 1, this is satisfied with other roots of unity, but the 6th root of unity has one additional property, namely that omega plus omega bar is 1. So if you think of the case where previously we had this at 2 edges between 1 and 2, this is usually when you have edges in both directions, you think of like having a non-directed edge because you can walk either way. So some people use name mixed graphs when you keep undirected edges and directed edges, but now this eliminates the need of using the undirected edges by itself, because you can just look at them as 2 edges in the opposite direction. So this omega plus omega bar is 1. This is the fundamental property that makes the 6th root of unity especially interesting in combinatorial applications. So that's the you can still do the same thing when you take powers of the matrix. You will count the number of walks. It works the same way, except that it's not the number of walks, but you have to put to each walk in the graph, you put the weight. So if you walk on the edge from vertex P to U, you put the weight omega on that. So you just take the product of this weights on the path, and then you count these weights of the overall possible closed walks. And that also gives you the trace expressions for these adjacency matrices. Now, the last property, which is also very unique, almost unique for the sixth root of unity, in addition to the fourth and the second, is that the characteristic polynomial of this Hermitian matrix has integer coefficients. So that's a special, quite special property in this setup.
Sorry, so you're saying for every
For every digraph, the characteristic polynomial has integer coefficients.
if and only if it's 2, 4, or 6 root of unity.
Yes, I think so. Yeah. So now you can ask the question we started with about spectrally symmetric digraphs. In fact, I will be speaking about spectrally symmetric orientations. The setup is that you start with an undirected graph, and then you ask, can I orient the edges so that this Hermitian matrix will have the spectrum which is symmetric about 0? So that's, it comes to the same outcome is true as for undirected graphs, that if your graph is bipartite, then any orientation will be spectrally symmetric. That takes a little bit, I mean, it's the same proof as in the undirected case. You just look at the eigenvectors, how they correspond to lambda and minus lambda. So that's, but it goes only one way. It doesn't go both ways. Namely, here you see two graphs in purple. They are not bipartite, but they are spectrally symmetric. So you see they have many triangles, so they are far from being bipartite. So what's special about this? Now, one interesting thing that I probably won't be mentioning later on is that if you take a tournament, so a tournament is orientation of a complete graph. So all edges are there. You take an orientation. If you take a tournament, you can never get spectrally symmetric. So you have maybe what I would say, it's too many triangles, but you will see later. So what the reasons might be. So anyway, the question is here, what kind of oriented graphs, orientations would be spectrally symmetric? Now, let me go back a little bit to the undirected case. This is Mantel's theorem. That's a basic theorem in extremal graph theory. Mantel proved it, I think, in 1909, or 1908, so more than 100 years ago. That's why it's an old theorem, and it asks, what is the largest number of edges in a graph that doesn't contain a triangle, a cycle of length 3? And the answer is pretty simple, but it's interesting. So the answer is that you can get up to n squared, so n is the number of vertices, n squared over 4 edges, which of course would be realized by the complete bipartite graph. So if you take n over 2 plus n over 2 vertices, all edges in between, it's a bipartite graph. It doesn't have a triangle, and then you have exactly, well, if n is even, you have exactly n squared over 4 edges in that graph. But if you add one edge, you will get, of course, if you add one edge to the complete bipartite graph on one side, you get many triangles. But if you have any other graph, not this one, it's triangle free, it cannot have more edges than this one. In fact, it was shown later by Erdős and others that if you have n squared over 4 plus 1 edges, not only that you get at least one triangle, you get linearly many triangles. Of course, you get, if you have this kn over 2 n over 2, you add one edge, you get linearly many, but this is true no matter what graph you take. So each new edge will give you linearly many triangles, which is kind of very interesting. So you're saying I'm getting more edges than half. This is roughly half of the edges, all possible edges, right? And then I get a triangle, and spectral symmetry fails, right? It's no longer bipartite. And so that led us to the question: can we do a little bit better in digraphs? And how much better can we do? So here is the definition of a density of a graph. It's maybe a little bit non-standard definition, but it's asymptotically the same. We look at any digraph on n vertices, and then we look at the quotients between twice the number of edges divided by the number of vertices squared. So the number of vertices squared would be with all edges, you would get n choose 2 edges, which is roughly n squared over 2. And twice of that would be, so that would be density 1. So the complete graph would have density 1. But here, like in this Mantel's theorem, you can go only up to density 1/2. That's the.
You're assuming that you don't have multiple edges going.
Yes, I'm speaking about, so, and from now on, I will be speaking about oriented graphs, which means that you have only edges in one direction or no edges between the vertices. So don't have edges, multiple edges or edges in both directions.
But you can still have oriented cycles.
Of course, yeah. So this is the question: can we beat 1/2? And you can see this example that it was a little bit bigger on the previous slide. Let me just pull back the right one. So this is this graph is K6. It's missing 2 edges, the two opposite diagonals, and so it has 13 edges, and then the density it's 13 over 18. So it's more. So 9 over 18 would be 1/2, and this is quite a little bit more than 1/2. So it's a very dense graph. Of course, maybe that's a sporadic example, right? So you ask, well, it's so small, so wouldn't take anything. But actually, the first step here is that there are no sporadic examples. If you get this one with 13 over 8, I can get huge graphs with the same density and still being spectrally symmetric. So what I do is I just take a blow up of the graph.
Just a small thing. The metric means lambda is an eigenvalue, then minus lambda is a.
Yes, that's the same multiplicity, of course, right? So yeah, that's the spectrally symmetric, yeah. Lambda is, if and only if minus lambda is, and same multiplicity, yeah. Yeah, feel free to ask more if. So here, the basic observation on this slide is that once you get one graph, which is pretty dense, let's say 13 over 18, you get infinitely many huge graphs, and the construction is very easy. In fact, you just take a blow up. So over you take every edge in a blow up, you take an edge in your digraph D, and then you replace it by you blow each vertex to L vertices, to L independent vertices, and then the edge would just be complete bipartite graph, keeping the direction from left to right. So all edges keeping the direction. So this graph, it's actually easily seen that it is spectrally symmetric, this blow up. Well, why is that the case? Well, the adjacency matrix is just the tensor product with the all one matrix. So just take the tensor product with the all one matrix, and the tensor product, so the eigenvalues would be just an eigenvalue of D times an eigenvalue of J, but J has only one all zero eigenvalues. So this is the full all one matrix, has all zeros except one, the major one, and it's still, well, it's not dependent on that, so it's clearly it is spectrally symmetric, right? Any tensor product with when D is spectrally symmetric. So, and then the density of this graph is the same. You just look at the number of vertices goes up by factor of L, and the number of edges, each edge now goes to L squared edges. So it's just keeps the density being the same. So the number of edges divided by the number of vertices squared keeps being the same.
Sorry, what was JL again?
So L was the blow up.
What is?
So D is you. So you assume D is a digraph which is spectrally symmetric, and
Oh, you're just taking. Okay, sorry.
yeah,
That's
you
right.
take this graph and then you just take with the
Yeah.
tensor product with.
All ones.
Oh yeah, so it's I so wrote K here, but JL. So with the all one matrix, okay, for the Hermitian matrix.
Yeah.
All one matrix of order.
Pardon?
All one matrix of order.
Yes, JL is all one matrix. It's
What?
not Hermitian.
L.
L or L by L, right? Yeah. Okay, so this is why this notion of density that we define is the natural one. So it's and then you don't bother with sporadic examples. You find one, you know, there will be many. So this is now the question: is there a bound on this the maximum density, like in Mantel's theorem? You get the maximum density 1/2 if you want to be triangle free. And here, is there an upper bound? Well, one thing that comes immediately is the following lemma. This works for any directed graph. And it says that a directed graph D is spectrally symmetric, then there is certain relationship between the count of number of triangles. You count T0 would be the number of transitive triangles. So these are the triangles which are not oriented cyclically. So would be from one vertex you would have two edges going out, or at one vertex you would have two edges going in. So this would be the transitive triangles. And the T1 would be the directed triangles, the number of directed triangles. So you look how many there are, and then you see that T0 must be equal to twice T1. And then you see in particular, this property says that the graph, which is spectrally symmetric, the number of triangles is divisible by 3, right? Because it's equal to 3 times T0. Every triangle is one or the other type, so it's 3 times T0. So so that's a necessary condition for symmetricity. But also it says more than just this. It says that if you have many triangles of one type, you have many triangles of the other type, right? So that's where that's what will be important for us. And the main result that I want to discuss is that actually we can find an upper bound on the density of spectrally symmetric graphs. So in particular, we don't get arbitrarily close to 1. So we have no tournaments, at least no large tournaments that would be spectrally symmetric. And the bound, it says that whenever the density of your digraph is more than 10/11, then it cannot be spectrally symmetric anymore. Now, the proof, it's kind of longish, so I've only prepared a couple of steps just to give you a feeling what kind of methods we use. It's very combinatorial, but so first to start with, so we start with a graph with large density. Let's say density is strictly more than 10/11, and we would like to show that something is wrong. So, well, in particular, maybe T0 cannot be 2T1. So that's, while doing this, we will be counting number of triangles, and it helps to do only, if you look at the number of triangles in a tournament, is n choose 3 of them. And it helps to say that we only look at the largest order term, n cubed over 6, and we may forget about lower order terms, because we may assume that the number of vertices is very large, so the lower order terms contribution will be much smaller than any constant times n cubed. So this is by the previous theorem that about blowups, and then we try to somehow to analyze the condition that T0 is 2T1. So here is the basic count that we do in the proof. You will look at all triangles in your digraph. Well, all triples of vertices. So there could be triangles of the two types. We denoted their numbers by T0 and T1. There could be triples of vertices that have 2 outgoing edges and 1 non-edge, and so on. So here you see the 7 possibilities for that, and we count how many. So here is the notation, how many of each kind we have. Now, every triangle is one of these types. So if you sum up the numbers, you get n choose 3, which, as I mentioned, is just essentially n cubed over 6. So and then we have the basic equality. Then the number T1 is big. T1 is equal to 1/2 T0. So we can eliminate T1, and we can also discuss how big T0 would be. You see, if you have a large density, there will be many edges. So the degrees of vertices in this graph will be larger than n/2. So if you look at the degrees of vertices, so here is some formula involving degrees of vertices, they will be large. Let me just show this fundamental equality here. I'm saying that the number of triangles counted as T0 is equal to the following quantity. You take for every vertex, you take its out degree and choose 2. So you take the sum over all vertices, or out degrees, choose 2, and then you subtract this number T2 plus. So why is that the case? Look at the vertex. Look at the vertex. This is any vertex here. It has some outgoing edges, some incoming edges, and the number of outgoing is dV plus, so the degree of V outgoing. And then you look at the edges among the out neighbors of this vertex, and they could be either in the digraph, and then what they determine this transitive triangles, because there are 2 edges which go out. No matter which direction this one goes, they determine the transitive triangles. And then you see that every transitive triangle is counted exactly once because it has 2 outgoing. There is a vertex with 2 incoming, and there is a vertex where you go through. So it's counted exactly once. And this gives overcount because we may have a non-edge between these out neighbors. but if we have a non-edge, this is already just counted with in this number T2 plus. So that's the fundamental inequality here that we use. And so once you come to this, what you can do? So it's we're trying to maximize the number of edges. So we're trying to maximize also this sum. So somehow this will be big. But on the other hand, if you take if you have this sum, so this sum, if you look at this sum, so there will be dv plus squared times 1/2. So this is dv plus squared times 1/2. And then if you do 2 times t0, you also get dv the in degree of each vertex squared. This will be twice t0 roughly. And you subtract these numbers of T2 plus and T2 minus. So now you want to say, what is the minimum possible value of this that I can get? You just use Cauchy-Schwarz, right? So by Cauchy-Schwarz, the minimum is attained when all these degrees and in degrees are equal to each other. That's the worst case. So you immediately just, even though you know nothing about these degrees, we just know they are big, you have a lower bound, right, on this. So you see there T0 is very big. That says T20 is big, right? And on the other hand, T1 is 1/2 of that, so, and that is something that goes wrong. So it takes 2 more pages to prove, but that's where something goes wrong if you have too dense graph. You cannot have so many directed triangles in there. So T0 is big, but then something goes wrong. So I'm not, yes?
Very quick question. So you can also write this sum in a third way, right? Because there are 3 types of vertices, like summation dv plus times dv minus t plus minus.
So there are here you see if you analyze the proof, we only use these edges among the out neighbors and the edges among the in neighbors, but not the edges in between.
Right.
So that is still a kind of something, but it comes in the proof that the extreme case is there will be no such edges in between, so, or all such edges in between. So that gives this kind of blow-ups that comes. So the extreme cases will be a type of this blow-up type that I used to in one of the previous slides. Okay, so that's the essentially what is wrong, and it took us. I was very happy when we came this. So we found first that tournaments cannot be spectrally symmetric, but here now we are in density far from the tournament. So it's 10/11 instead of 1. So it's just far from that.
Sorry, and what's the lower bound? Is it 0?
Lower bound is this. This is the worst. The lower bound, 13/18 that I showed. That's the one. That's the worst one we have. So we tried with computers on small examples. So up to 7, 8 vertices. This is actually the best we could get. But there could be some on 19 vertices.
You have to have connected graphs, is it?
If you're not connected, then density is very low. So yeah. So it's not a deal.
So among connected graphs, the lowest we have is 13/18.
So this is the largest density that we know of existence of a graph, which is spectrally symmetric and has this large density, 13/18.
Okay.
Yeah. So
it means strongly connected. Strongly the diagram, right?
Well, in this density, it will be strongly connected. So it's almost, you could prove that. Now, to end up, I would like to mention few interesting examples, maybe. So two examples that we had. We had to look at tournaments of order 9, especially because the proof wasn't strong enough to give this 10/11 for tournaments of order 9. And then it turned out that there is one tournament of order 9. You see, when we do the triangles counting, this is only the third moment, the third trace of h cubed. And then you ask, oh, maybe I could use trace of h5 as well, and that would give me something better, and even trace of h7. But there is one example where all these odd traces are 0 except the 9th trace of h to the 9. So it's basically it's going over Hamilton cycles in this 9-vertex tournament. So and that one is non-zero. So it's interesting that the trace of h cubed and h5 are not sufficient for this, even with such a large, even on tournaments. And then on we have two examples. We have the complete list of examples on 6 vertices, but these two examples are a little bit strange. So it's they are spectrally symmetric, and if you replace this edge hanging out with any tree, it is still spectrally symmetric. Now, if you do it on the other one, it's not. So that's it's a bit strange, right? Why this is the case? So, and it shows there are some subtleties in this that you need to consider. So the reason for these graphs is this one has a vertex. So this is a vertex which is connected in every odd cycle. So if you remove that vertex, the graph on the left would be bipartite. Well, it would be just a star. And so you can add a tree to it. So, but the other one, if you look at that vertex where you would put the tree, it's no longer has the same property. So it's if you remove it, you still have triangles, right? It's yeah. So there are subtleties, and maybe that would be probably the thing to end up. This was just one case how going from graphs to digraphs can give an interesting problem. We're still looking for further applications, right? But it's been asked. So you can ask many questions which you know about the undirected graphs on these Hermitian matrices. It's the Hermitian matrices have one particular property that is very useful when you relate to combinatorics. This is the interlacing. So interlacing still holds for Hermitian matrices. So that's the powerful. You lose Perron-Frobenius. That's the necessary thing. With this, I'd like to stop. Thank you for your attention.
So in this case, can we also define Laplacian matrices equivalent to Hermitian adjacency matrices?
Yes, you can, but it's so you could do this. Simplest Laplacian would be to take the sum of the. So you would like to get 0 as the smallest eigenvalue. So you would take diagonal would be sum of the off diagonal elements, and then take minus Hermitian matrix, right? That one wouldn't be necessarily Hermitian, but it would be if you have a regular, not necessarily regular, but every vertex has the same out degree as in degree. Then the sum will be an integer, so would still be okay. So it's not clear exactly what to do. I think even in this special case where every out degree, every vertex has the same out degree as in degree, then it's obviously what you can do with the Laplacians, and this would still be a useful case.
Also, how many equivalent results can be proved from Hermitian adjacency matrices to original undirected adjacency matrices? Like there are many known results for them now. So can you like translate them using these matrices for digraphs?
Well, you get a variety of different results. So this if you think of mixed graphs, or you think of edge with double edges for undirected graphs, so this extends the undirected graph analysis, right? So, but and then some results extend with more difficulty, like the one I was talking about today. But yeah, not every result. So, like the spectral radius could be the largest negative eigenvalue. It's not, there is no Perron-Frobenius, so it could be that the negative eigenvalue is larger in absolute value than the largest positive eigenvalue.
And also just one question. So here this HQ which we are taking off Hermitian matrices, right?
Right.
So in this one also it counts number of walks if you take powers of Hermitian adjacency matrices.
Right, but with this notion of the weight of the walk, right? So you like I did for triangles, I had the triangles here. If you have a transitive triangle, then you have, if you go in, let's say you go in this anti-clockwise direction, you have omega times omega bar. So the product of them is just omega, right? So you take the triangle, and then with this weight omega, you sum up all this. So not just numbers, because it's not one, it's omega. And then for the other triangles, you get weight -1, so you get negative weight. So it's counting, but it's counting with weight -1. So you count these closed walks with the weight, and the weight is you take you go on the closed walk. You see if you go positive direction, you take omega. If you go counter direction, then you take omega bar, and you take product of this along the walk, right?
Thank you.
How did you guess this omega?
Pardon?
Sixth root of unity. How
Yes.
did you guess that?
Well, just this is
No other complex number works.
right. Yes, this is the property 2 is was the turning point. So that's you can, of course, you can do more general things, but for combinatorics they will be less interesting. So I think so than this one. Yeah.
Can we say if these odd cycles, they have weight W in the graph?
So if you have an odd cycle in a graph, there it's a product of omegas and omega bars, right? So, and then if you have omega and omega bar, they, I shouldn't say cancel out, but the product is 1, right? So, and that will just take 2 edges. So yeah, the product on an odd cycle will always be omega or omega bar, right?
If in the graph, all the odd cycles, they have weight W, then can we say it has that property symmetric?
Well, it won't be, because if you go one direction around, you get omega. If you go the other one, you get conjugate value always. So you get omega bar in the other direction. So it's that's why also the contributions for the determinant, so for the characteristic polynomial, cancel out. You get omega and then omega bar in the other direction. So that's why you get these integer coefficients, real integer coefficients for the characteristic polynomial.
Okay, so let's thank.
Thank you, sir. I request Dr. Debajit sir to honor Professor Bhojan Mohan. Sir, please. Thank you, sir. I thank Debajit sir for chairing this session. We'll have a tea break now, and the next session will begin at 11:50. Thank you all.
Okay. So you look at the medicine price as over that sort of reminds asymptotic relation between the name from market. This is right. So triangle concept. So can you sort of do some bounds on what that will happen with the topic item?
Yeah, I think
The external community, of course, you care about. Yeah, I see the right half rather than one. As an analyst, I would say you can look at, or I would very comfortable. So you look at the nth root of everything, then you plot the maximum density of the function. Then realize the problem. Simple analog condition. Hello. Current to right hand is different. That is completely positive. So positive is with all the coordinates are except positive, then x is really. Yes. X is r plus b. But Acha. And pole is just the scale, positive scalar, k intercept minus k scalar. K plus k contained. Okay, ना पे पड़ेगा. Fine. You can have a smaller dimensional. K can just be one dimensional. Yeah, to that n dimension figure.
Right.
Okay.
It is more than gate over. When you have that level, and that's now I particular topic. Business is positive plan. I just think there are concepts. Observatory are easy to buy this. Go positive for the go positive also. Provided came to
K को positive is the positivity. Cool.
Basically, the standard there are T and T was both here is to the then in the onto the positive natural language with the automatic. And T was positive.
Bijection बरोबर. इन्व्हर्स आहे म्हणजे bijection आहे.
In fact, जर मी फक्त on to बदल केला A को positive and A को positive. So automatically एक तरह से T bijection. In general, T injective is the automatic.
And all these are linear.
They are the most then how question of another keep on to the question October 5 for this is the
You will apply, you will have.
Capable. So that's they are not was it a company? Then it is a standard text and concentration. Because it is the performance values of our work and it's our okay, I have basically stated that this figure is only target which is actually not true. Over. Not true on this. And I have got a characteristic shows that if there's any of the answers, I mean, just will take you to the character of but apart from this, the rate of the month, त्यानंतर चेतावणी
Rotating the paperless sheet of the linear preservers of cost.
Then you got the big point. Just like if points already put up, package up. UP prime is 130%. Dual. This is a dual completely possible. That's we thought about two families. So those are prime and they are related. Our purpose is the D graph of the big graph is
okay, very good.
Someone could then hear that.
Any classified
Already. Even they are not intended to charge.
Oh,
then they somehow and in another shit of that is a particular grade and
anybody.
And it is
Put a header directly.
Direct.
When it locally made by just firm they started doing from scratch.
The point I'm saying is on it's complicated for the event. Carrying often positive general and the automorphism is considered largely. The automorphism of course for this one some of the middle this type of जेणेकरून तुम्ही तुम्हाला हे काढणं सोपं आहे जर तुम्हाला
it doesn't prove that each of these things satisfy.
That's the thickness such a class of operator. Just take a
but then sure, but then you have to then there are two methods. One is you have get a definition given by this is equal to
not equal. It's contained in this.
that you know what it is. That is that is part second part, the easy part. But you also prove that this is equal
invertible. All invertible is equal.
Okay. That's invertible.
Invertible.
Sure.
Okay. Same case with this point.
Very good. That is.
So in between space not where these are more. This one more.
Okay. So at least you'll get a new character. How easy it is to calculate these around. Oh. त्याच्यामध्ये मग invertible character First we find it wrong. It will not be inverted in this term.
If you assume bijective,
Okay, bijective नहीं है.
ये पण वेगळं येतं.
पण तुम्हाला on to साठीच करतात.
The reason of the benefit management also मिळाली. आम्हाला काय सगळा सेटअप होता ना तो so example reserve करू. आता इसका पॉइंट आता है की कागज पे लिखने पड़ेगा. और मोटर क्वेश्चन. क्या जो इंटीग्रल रिजर्व का क्वेश्चन है तो बराबर.
गौडाने ते सगळं केलंय. रिडिराईट गौडा रिझल्ट जनरलाइज नाही करताय पण म्हणजे इझियर वेगळी मेथड नसेल त्यांनी सोपं.
मेन पॉइंट आता है कि
the method is the selling point and these are very nice. Very
basically सगळेच बोलतील ना मोठा
to all the possible.
For instance,
In general.
for example, this is RS.
Right.
Non-negative matrix. In general, infinite dimension.
The span of each are equal. Includes the positive. The positive span includes the equals the positive. माझ्याकडे ग्रांट तुम्ही येतो काही दिवस
I believe now what we know, work is for
नाही आपण तुम्हाला पत्र लिहिलेली यावरांनी तरी महिन्यामध्ये मीड फेब्रुवारी कारण त्याच्याआधी हाय दोन पगार माझ्या आई वडील सुद्धा तेव्हा फेब्रुवारी काम वाटायचं they have to send me from that. So they said that maybe second week of February. April middle for a time. They spent on these at the game. February second week of
Hello.
Open the magic to charge the bike of
Okay.
yes, there are no special
पैसे आणि सायन्स मग मी लोक काय करू लिमिटेड कनेक्ट होतं
ಈ ಫೋಟೋಸ್ ಕ್ಯಾಮ್ರಾ ತೆಗೆದು ಫೋಟೋ ಕಳ್ಸಿದೆ ಅವರಿಗೆ ಮೊಬೈಲ್ ತೆಗೆದು ನಾನು
Welcome everyone for the next session. So this will be chaired by Professor Mika Mathilas. Over to you.
Thank you. So, it is my great pleasure to be the chair of this session, and I would like to introduce our first distinguished speaker, Professor Rafiqul Alam. And Professor Rafiqul Alam is a professor in the Department of Mathematics at the Indian Institute of Technology, Guwahati. He earned his PhD from the Indian Institute of Technology, Bombay in 1996. His research focuses on linear and numerical linear algebra and spectral perturbation theory. He was awarded the Voicecast Fellowship from DST, Government of India, and a visiting fellow position at TIFR Bangalore. Professor Alam has been an invited speaker at numerous national and international conferences and workshops. Please join me in welcoming Professor Rafiqul Alam. Over to you, sir.
Thank you. At the outset, I'd like to thank the organizers for the warm hospitality, and especially to Professor Prasad for everything. This is a joint work with Volker Mehmet from TU Berlin and Ninoslav Druar from Croatia. And let me come to quickly the problem. So this, I'll consider the second order systems of ordinary differential equation, where this is associated with what's known as the damped mass spring system. And this equation is very special because the matrix M, which is n by n matrix, M, D, K, these are all symmetric. M is usually positive definite, but there are applications where it is positive semi-definite. The K matrix is usually positive semi-definite, and the damping matrix D is semi-definite. It could be either positive definite, positive semi-definite, or negative semi-definite, and F is the external force. So this is basically, it describes a mechanical system. And in order to understand the natural frequencies of a mechanical system, what one does is that you set this external force equal to 0, and then you have a mechanical systems, and then try to understand its internal frequencies. Okay, and so setting that equal to 0, what we get is this one. This is homogeneous systems of ordinary differential equations. Okay, so if you take a solution of the form this x that's given in terms of exponential, so the lambda is unknown scalar and u is a fixed vector that we need to determine so that we have a solution of that form. So if I put the value there, then we get this quadratic matrix equation. So it's a very, very special equation where the coefficient matrices are all Hermitians, and apart from that, M and K, they are both positive semi-definite, and D is semi-definite. So this problem is important because either this mostly this if you have a mechanical systems or the mechanical and electrical engineers, they use this model to design buildings and bridges, and then the D matrix is known as damping. It tries to control the vibration. So a standard method to solve this is, because this is a quadratic problems, and this quadratic problems is usually difficult to solve because it doesn't have any canonical forms such as like sure forms, or in case of linear case, the Weierstrass canonical form. So what you do here is that you apply this technique, what's known as linearization. So this quadratic eigenvalue problem here, can be reduced to a linear eigenvalue problems in higher dimension. And this is one example. For example, here this X matrix for any non-singular matrix X, you can basically reduce this to a linear problem and then solve the linear problem. There are, one can use MATLAB to solve. But here it shows some amount of arbitrariness. The X is any non-singular matrix. And this is a very, very special problem. It has a lot of interesting properties. So when you do this transformation, many of those may not be preserved. Okay. So the idea is try to find this linearization. So this is a separate problem that preserves the structure of the original problem. Okay. So this is how this needs to be solved. So let me now, this is the background. I'll come to the main problem. So let me now fix some notations. So this P lambda will always denote this quadratic matrix polynomial, which I'll call this MDK system. Okay, I'll assume this to be regular. That means the determinant of P lambda is not identically equal to 0. Okay, and M and K are positive semi-definite, but I assume that one of them must be positive definite. Otherwise, no, we cannot, right now, we cannot handle both to be single. And D is semi-definite. Usually, I assume that it is positive semi-definite. The result is same for negative semi-definite. So 0 is an eigenvalue. Okay, so the eigenvalue, how do you get? Take the determinant of P lambda, set that equal to 0. So complex number, those are the eigenvalues. And but here you can have infinity as an eigenvalue also. But you can see that 0 is an eigenvalue of P lambda if and only if K is singular. On the other hand, infinity is an eigenvalue if and only if M is singular. The spectrum, I'll denote by this capital lambda P, set of all eigenvalues including infinity. So first consider this undamped system. So this MDK, if you set D equal to 0, there is no damping, then you have a mechanical system. Okay. So M and K, I'll assume henceforth that M is positive definite. And then we can choose a congruence that will diagonalize both M and K. And in fact, we'll have this. Okay. So this is, I can choose this I have. And from there, immediately we get purely imaginary eigenvalues. Okay. If I assume that K is also positive definite, all will be purely imaginary. And if K is semi-definite, then okay, 0 also will be an eigenvalue. So this is undamped systems. Everything is known here. The idea is to choose damping so that you have control on this eigenvalue. So, okay. So if you choose a damping now, in practice what happens, the damping matrix D is semi-definite, but it has low rank. Okay. And the moment you add this damping, the sum of this purely imaginary eigenvalues will move. So important to characterize which eigenvalues will move. Okay. And once it moves, normally what happens is the problem that I'm going to describe is that since my co-author, Ninoslav Brohar, he had an industrial project. So he had this MDK system, low rank damping matrix D, but it has large magnitude. So without damping, the eigenvalues, they are all on the imaginary axis. Okay. So when you add the damping, so positive semi-definite means the sum of the eigenvalues move to the left of complex plane. And because of the symmetry, they lie on the semicircle, the complex plane. Okay. So what you observe that you choose a damping and then say one imaginary eigenvalue move to the left hand side. It moves, okay, in a semicircle, and its mirror image from below that also moves, and then they'll coalesce on the real axis, real line, and they form a double eigenvalue. Or in case it's multiple eigenvalues, so that we'll have even order multiplicity. And then when you further change, then the real eigenvalue, the stays remain, and one goes to minus infinity, another goes to 0 as the magnitude of damping increases. But he's observed that numerically from his applications, but he was unable to explain what is the reason. And so we had this problem that to try to understand how this eigenvalues of this MDK system it evolves. It's a very classical problem used by mechanical civil engineers. But then this is the problem that he found. That's how to explain that. Okay, so that was the main reason I started looking at it. So you have this undamped system, add a damping term, okay, and then you see that some eigenvalues will move, some perhaps will stay, this undamped eigenvalues. So there are actually three types of critical eigenvalues here: 0, infinity, and purely imaginary. Okay, they are on basically the boundary of the stability region. The solution contains exponential, and if you want asymptotic stability, then we should not have eigenvalues on the imaginary axis. So these are critical eigenvalues. So first we try to understand how they will behave, okay, with respect to the damping matrix. And then I'll come to this real eigenvalues. Okay, so first thing was that from the point of view of modeling and especially from the point of view of numerical computations, the 0 and infinity eigenvalue they create problem, especially infinity eigenvalue problem. Numerically, there is it pollutes the accuracy of other finite eigenvalues, and modeling and theoretically it also plays an important role. So my other co-author Volker Merman from TU Berlin, so he had a project from a high-end car company. So what the problem they had is that you have expensive cars, you drive for a few hundred miles, and then their braking system started making noise. Okay, so it's called brake squirrel problem. So he had that project to fix that. Okay, so what he found that the models that they use for designing this braking system, it has this MDK system, but AM was singular, positive, semi-definite, but singular. Okay, and so it had infinity eigenvalue. So the infinity eigenvalue is problematic from the modeling purpose. Also, as I said, that the way to solve this problem is through linearizations. So if you have infinity eigenvalue, many times it prevents you to get structure preserving linearization. So the idea is you try to deflate it, okay, infinity eigenvalue. So the one way is if M is singular, you make small perturbation, it becomes non-singular, infinity eigenvalue vanish. Okay, but that doesn't work because if you perturb M, it is going to perturb other eigenvalues. Right? So the deflation, why you want this deflation? Because you do something to this original equation so that infinity is pushed out, but everything else will remain undisturbed. Okay, so that's called the structure preserving deflation. So all the structure that I have, M, dk, the structure should be preserved, and only 0 or infinity eigenvalue we have to move out without disturbing other eigenvalues. And then purely imaginary, once that is done, then you can deal with purely imaginary eigenvalues, move them out so that system will be stable. Okay, and one is through deflation, and the next is that once you have deflected, it may not remove all the purely imaginary eigenvalues. So what do? You add some small perturbation only to the damping matrix. So you can fiddle only with the damping matrix. You don't touch M and K. Okay, so no perturbation on that. So fiddle with the damping matrix, and then you try to move the purely imaginary eigenvalues again without disturbing remaining eigenvalues. So you have the targeted eigenvalue that you want to push out. Okay, and finally, once this deflation is done, 0 and infinity, now then the matrix reduces to polynomial matrix polynomial I have considered. Okay, it has some additional properties which is called the hyperbolic polynomial. So I'll come to it later. Okay, and then try to understand its inertia. Okay, and the types of eigenvalues. As I said, the eigenvalues some move to minus infinity, some move to 0. Okay, it depends on what kind of eigenvalues you have. So we'll discuss that at the end. So this is deflation of 0 infinity eigenvalue, right? So infinity is an eigenvalue of the original polynomial if and only if 0 is an eigenvalue of the reverse polynomial. Okay, so without loss of generality, I can describe deflation of only 1. So I'll assume that okay, infinity is not an eigenvalue, 0 is an eigenvalue. So we cannot deal with both. Okay. So assume that 0 is an eigenvalue, and same technique will work for infinite eigenvalue. So henceforth, I'll assume that M is positive definite, K is semi-definite, okay, but it's single. Alright. So the first result is this. You take this, since K is positive semi-definite, I can have this factorization, rank factorization, GG, I can write K to be equal to GG star, where G is n by P matrix, it has full rank. So once I have that factorization, consider this pencil S lambda, which is a kind of linearizations. So original linearization, if I apply, I'll have 2n by 2n matrix pencils. Here I have n plus p by n plus p, smaller size, and original linearization, it will keep the infinity zero eigenvalue, but here I want to deflect that. So this is the pencil we have, which we can solve in MATLAB, okay? And this pencil S, okay, and the original polynomial, they have the same non-zero eigenvalues, okay? The zero, anyway, that we are trying to get rid of. Not only that, everything else is preserved, which can be, precise statement can be given in terms of Smith-Macmillan form of this P lambda by lambda and the Smith form of S lambda. So it says that not only the eigenvalue, non-zero eigenvalues, they are preserved, their algebraic multiplicity, their geometric multiplicity, their partial multiplicity, everything else remain undisturbed, okay? And this keeps the bijection between the null spaces. So eigenvector from S lambda, its pencil, from its eigenvector, we can recover the eigenvector of the original polynomial. And if D is definite, so the dumping matrix that we are choosing, if that is a definite matrix, then we don't need to do anything. This whatever linearization I've taken, it simply deflects the zero eigenvalue. So the whole thing stops here. But as I said, in practice, the D matrix is not positive definite, it is semi-definite, it should be singular. Okay, so in that case, so this is the first case that deflects the zero eigenvalue if the damping matrix is definite, either positive definite or negative definite. But if it is positive semi-definite, then again I'll consider this, and then what do you do? Add one more step. So this is compute QR factorization of the G matrix, okay, and then partition this Q. Q is unitary, okay, Q is unitary matrix. You partition it and call this Q1, that's the first P columns of Q, and Q2 the last n minus P columns of Q, and then we can check this, we can do this test. So if D is semi-definite, then look at this matrix Q2 star D Q2. If it is definite, then again S deflects the zero eigenvalue. Okay. The other test is both D and G, they are rank deficient matrices. So from this matrix D and G, okay, look at the rank. If the rank is n, then again the pencil that we have considered, it deflects the zero eigenvalue. Okay. So either we can have these tests, but still but then question is what happens if this is not definite, for example, if this is semi-definite and this also has rank less than n. Okay, so that's the final case. Finally, what I can do is that, so suppose that the rank of D, this matrix that we have, is n minus r. Okay, in that case, one can prove that 0 remains an eigenvalue and its multiplicity is at least r. Now, if you take this QR factorization, okay, of the matrix this DG, and this QR, it's not just ordinary QR factorization, you take QR factorization so that this particular matrix, it has full row rank, which can be done using this QR factorization with column pivoting, and form this matrix D11. This is the matrix, okay, and perform this unitary similarity transformations on M, and then partition M and calculate the Schur complement of this matrix M22. Okay, and define a new pencil here, H lambda. Okay, so this is a smaller size pencil than the previous pencil S lambda, and define the corresponding polynomial. Okay, so this one is actually This is the polynomial, this becomes trim linearization. So in this case, this M hat is positive definite again. And so what happens is that we are getting another MDK system where this is positive definite, that is semi-definite, and this GG star, that's also semi-definite. Okay. So this pencil is actually congruent. So we have this congruence X. Okay. So it is congruent to this block diagonal that is on the right hand side. So this exactly shows that the zero eigenvalues are appearing here. This pencil and S lambda, they have all the non-zero eigenvalues, they have cell. Okay. And this particular pencil now completely removes the zero eigenvalue. So H doesn't have zero eigenvalue, it is deflated. But this polynomial P hat that we got here, it still may have zero eigenvalue. So the zero, if you go to the quadratic polynomial level, is very difficult to get rid of zero unless you have very, very special assumption. So additional assumption is that this R was, if you remember, the rank of DG n minus R, that R and P, which is the rank of G, if they add up to n, in that case, this polynomial, again, there is no zero eigenvalue in this polynomial. So you can go back to the original one. So this is basically the theorem. Okay, we will have its corresponding algorithm. And here we can, no matter what, we can remove the zero eigenvalue, and hence taking reversal, I can remove the infinity eigenvalue. So this is the first result that we have. Okay, so the semi-definite assumption that we have that cannot be dropped. This is the counter example. Okay, you can see that D is indefinite matrix, and you have this conditions DG rank equal to 2, but still it has zero eigenvalue. So it's important. So this is that we have given two algorithms, one based on QR factorization, another one based on singular value decompositions. And this, since SBD based algorithms are better numerically, so here I have not given the mathematics behind this algorithm, but so it uses basically singular value decompositions and then constructs the pencil H. So you have tested this one to this problem. Again, this problem comes from Nino's project. Okay, so he was basically analyzing vibration of a rod. So this is the partial differential equations, and then you have to do this weak formulations, then separation of variables, then apply finite elements, and so finally it reduces to this quadratic homogeneous equation. Okay, so for this example, the size of n is 1602. The rank of the matrix M is 1599. So you have three eigenvalue, infinity eigenvalue, its multiplicity is 3. So this is a problem where infinity is an eigenvalue. And the task is to get rid of infinity. So what we have done, that we have taken the reversal. Okay. So in this particular, taking the reversal, I'll have zero eigenvalues. So we use MATLAB without doing anything to calculate zero eigenvalue. We got the smallest three eigenvalues are given 1, 0. This is, you see, of 10 to the minus 2, another one is 10 to the minus 19. So numerically they are treated as zero eigenvalue, and therefore we need to get rid of that. All right. So use that algorithm and then again calculate the eigenvalues of reduced matrix, and the smallest eigenvalue, absolute values given there, and the real part. What happens is MDK system, all the eigenvalues will be, I'm choosing, if you choose positive semi-definite, it will be on the left hand side. So this real part and its maximum, you see, is around 0.45. So it also preserves the stability of the solution. Okay, so let me now come to the purely imaginary eigenvalue problems, and then how to deflect that. So in this case, again, I'll consider the MDK system, and this P naught lambda, it now denotes the undamped system M and K. Assume M is positive definite. K I can assume in this case to be Hermitian, but again I'll assume it is positive semi-definite. So this is the first result. So if you apply this, so this is the undamped problem, okay, and then you are choosing damping. So if you choose damping, yes, 5 minutes. So if you choose damping, okay, so which eigenvalue will move? We can characterize that, okay. So this is the characterization. So Iwsmga is an eigenvalue if and only if the rank is less than n. And any purely imaginary eigenvalues, okay, that this P may have, these are basically undamped eigenvalues. So originally you have purely imaginary eigenvalues, you have added a damping, some would move, some will stay there. Okay, so those are eigenvalues. So the only thing can happen is that its geometric multiplicity might be reduced. Okay, so this is basically the algorithm that we have based on this result. So you compute QR factorization again, and then partition Q, and then there is some complicated construction is given here. I want to construct a congruence, right? So this X matrix that is given X1 and X2, this is the construction. It shows that, okay, this if you apply this matrix, then you can see that this P tilde hat that you have and purely imaginary eigenvalues appearing here, okay? So it is basically deflecting. So the matrix P lambda and P hat lambda, from there, they have the same eigenvalues except those plus minus I omega. Okay, so since I don't have time, I'll just quickly go to this main result, okay? So that was basically deflections. And then there is this targeted perturbation I just skipped. So normally what happens is that this is what we got in the previous result. And if I add some perturbation here, okay, in the D matrix, and then this eigenvalue evolves as an eigenvalue of that particular polynomial. And that's a very, very special polynomial. Okay, so this is the algorithm based on this SVD. It requires two SVD, two Cholesky factorizations, and solution of two systems. And we have considered this example, 10 by 10 example, which had 20 eigenvalues. So there are plus minus 7i, plus minus 5i, those are the eigenvalues, and 2, 0 eigenvalues. We have used this algorithm, okay, and wanted to deflect this plus minus 5 and compute the eigenvalues. And you see this, these are 18 eigenvalues. This is not there. 7i has become, there is some small, tiny real part, which is because of rounding error. And instead of 2, 0 eigenvalues, we have these two eigenvalues we have given, which are very small. Okay, this inertia, I will not be able to, this part is quite non-trivial. Okay, so I just want to show one result. So these are what's happening is that the pencil that we have, first I had a quadratic polynomial, then I moved to a pencil, from there I moved to a matrix. So taking Cholesky factorization of M, I can construct a matrix. This matrix is structured. This is actually J Hermitian matrix, or this is also called pseudo Hermitian. It has many interesting properties, and this also gives you, so the standard, the eigenvalues of this non-zero eigenvalues are same as the non-zero eigenvalues of the given polynomial, and it will deflect the zero eigenvalue if this rank condition is satisfied. Okay, and I have basically defined, I said that the Lino's problem was that the real eigenvalue, one is moving to the minus infinity, another is going to positive infinity. Its explanation can be given through this. Now, as a real eigenvalue, you define a type. Okay, look at the eigenvectors. Okay, and then from this, take the matrix that gives the basis, and then take this matrix X star Jx, and look at that whether it's positive definite, negative definite, or indefinite. Based on that, we have positive type, negative type, and mixed type eigenvalues. And that, there are several results here. It looks quite intimidating. It gives you inertia eigenvalues, number of positive type eigenvalues, negative type eigenvalues. It gives, okay, from which you can determine this. So finally, I wanted to come to this result. Okay, so you take this matrix A, we have moved to the matrix, compute this eigenvectors, and form this quantity. From here, I can compute this. Okay, these are basically this plus and minus, they describe the positive type, negative type eigenvalues. And then if I calculate this particular quantity, okay, so we have this. So if this quantity is positive, this delta U is positive, I mean the real number and positive, then we have this mu plus minus negative, and mu plus gives a positive type eigenvalue because this quantity becomes, this is negative and that is negative, so this is positive type eigenvalue. Similarly, you have mu minus negative type eigenvalue. If this one equals 0, that gives you mixed type eigenvalue. And the QT, if I showed you earlier that through perturbation, so this matrix, I can basically calculate this, those things, and I get two eigenvalues. And from here, you can see that this mu plus, you have this denominator, take t tends to infinity, it goes to minus infinity, okay? And this one goes to minus infinity, and this goes to 0. So it shows that two real eigenvalues, they are moving, they're staying real. They don't move to the complex plane again, okay, because of the type. So one goes to minus infinity, another one goes to 0. I think I'll stop here.
Thank you, Professor Alam, for interesting talk. So we have some time for questions and comments. Do we have any? So it seems that we don't have any questions, but let us take Professor Alam again.
Now I request Professor Mika Matila sir to honor Professor Rafiqul Alam sir. So please.
Okay. The next speaker in this technical session is N. Agambram from former DDG CSO Delhi. And the title of his talk is Disjoint Sections of Positive Semi-Definite Matrices and Their Applications in Markov Models. And now I will give a short introduction for Dr. Agambram. So, Dr. Agambram is a former Deputy Director General of the Indian Statistical Service, Government of India. He completed his Master of Science in Statistics from Annamalai University in 1976 and earned his PhD from the Indian Statistical Institute, New Delhi in 1989 in the area of generalized inverses of matrices and linear complementary problem. His research focuses on generalized inverses on matrices and its applications. He served in the Union Ministries of Agriculture, Industry and Statistics, retiring as a Deputy Director General Statistics in 2012. He was deputed by the International Monetary Fund as advisor on national accounts in Bangladesh 2014 and 2015, and has recently served as guest faculty at IIT Madras and currently teaches mathematical finance at IIT Tirupati. Please join me in welcoming Dr. N. Agambram. Over to you, sir.
So the topic of my talk is Gauss Markov models using ICM method. The Gauss Markov model is a classical model. It has applications in the multivariate analysis. Originally, Gauss started this from the method of least squares. It all started from method of least squares. And later on, Markov contributed to this. And so this is called Gauss-Markov model. Now in this model, the covariance matrix if it is non-singular, there is no problem, much of a problem in the analysis. If the variance covariance matrix is singular, then it creates several problems. And one of the methods, one of the ways of tackling this issue is to use G inverse. Dr. Rao has his major contribution in analyzing this Gauss-Markov model by using Z inverses. Now, even when he is using G inverses for analyzing this Gauss-Markov model, at several places you find he uses Lagrange multipliers, differentiation, etc. And we find that he has devoted one full paper representation of blues in Gauss-Markov model, in which the notations he used seems to be complicated. And one doesn't understand what is going on there clearly. We cannot picturize it in our mind to understand that. That is my personal understanding. And Rao's linear statistical inference, if you see that book, I find at least 30% of it is devoted this method of least squares Gauss-Markov model, because it is linear statistical inference concerned with multivariate analysis, and naturally this Gauss-Markov model comes into picture, and he has devoted minimum 30% of his work in the linear statistical inference book. That's what I find. Now, interest in research in this Gauss-Markov model continues. Even I find papers in 2024 regarding how to estimate, how to get estimators of blues, best linear unbiased estimators of the parameters in the Gauss-Markov model. So recently, I published a paper on inverse and complemented matrix. I call it ICM. This ICM method helps us to unify all these methods so far in this Gauss-Markov model, in this analysis. It is a unifying method. So I want to present here how we are able to unify those previous methods by using this ICM. So we'll briefly say about generalized inverses of matrices, all of you know. Then inverse rank complementary matrix, what it is, I will tell you. Then what is a section of a matrix? This is a term that I introduced. Section of a matrix. What is a section of a matrix? Then this GGM. And for analyzing this GGM, I am going to decompose Y into uncorrelated random variables, so that each part of the component of this uncorrelated random variable will be confined to only that X beta. That is an essential part of it. The other thing is irrelevant. So that helps us to analyze it better. Then we'll compare IPM of CR Rao and our approach. Then, as I mentioned, when G is singular and further complication arises when range of X is not contained in a range of G. Some part of the range of X goes out of range of G. So that is further complication. So how to deal with that? Then the representation of blue of x beta, various forms of the estimators of x beta. Then how to estimate in general lambda transpose x beta on condition that h beta is set. See, one problem is how to estimate lambda transpose x beta. See, take lambda transpose x as p transpose. Usually the linear function p transpose beta, how to estimate. I take this p transpose, I say lambda transpose x, so that p transpose beta is estimable. The function, linear function p transpose beta is estimable when there exists a lambda such that lambda transpose x is equal to p transpose. So instead of p transpose beta, I straight away say how when lambda transpose x is x beta is estimable. So once you find estimator of x beta, you can get all estimators of all estimable linear functions of beta. And here already a condition is there that h beta should be equal to psi. Under that condition, what is the estimator of lambda transpose x beta? Then we'll see how to use method of least squares for estimation of x beta. There is in linear statistical inference book, you find the unified method of least squares for estimating x beta. So let us see how we'll use our method. So then we'll see what can be studied further. So you all know what is G inverse. The X satisfying the first equation is called G inverse. If it satisfies the second equation, it is the outer inverse. If Ax is symmetric, then it is least square inverse. If Xi is symmetric, it is minimum norm inverse. And the X satisfying all these four equations is Moore-Penrose inverse. Now let us come to what is called this inverse rank complemented matrix method. There are several methods for computing G inverses. There are different kinds of G inverses with different properties. And there are different unified methods for computing all these G inverses. Now, we are going to see one method is inverse rank complemented matrix method, which is also a single method for getting any kind of G inverse. Now, in this method, if you take the matrix A square matrix A, it can be a singular matrix. You find a matrix C, which I call complement of A, so that A plus C becomes non-singular. The A and C are disjoint. Now, suppose A I can write as A1 plus A2. Then A plus C whole inverse, I can write as A1 bar C plus A2 bar C plus C bar. So corresponding to A1, A2, C. In this A plus C whole inverse, you get A1 bar C, A2 bar C, and C bar. What are they? Now, to prove this, you can follow this method. It is only by means of rank factorization. You can just get those components. Now, the same A1 bar C, A2 bar C, C bar, they can all be obtained from this. AI bar C is equal to A plus C whole inverse, AI into A plus C whole inverse. This also you can check now there. So each part, A1 bar C, A2 bar C, C bar C, can all be obtained in this process. A bar C is something like this. If you want to have the proof, proof is by means of rank factorization. That I have indicated. Now, in this method, you see A1 into A2 bar C is equal to 0. If you take the cross products, A1, A2, C, A1 bar C, A2 bar C, C bar. In these first three factors, the second three factors, if you take any cross product, that will be 0. That is A1 into A2 bar C equal to 0, A2 bar C into A1 is 0, all those are such cross products. They are all 0. And directly if you take the product A1 into A1 bar C, that is an idempotent matrix. Now, one more extension of this ICM. Now, suppose you take a B. Take a B. B is equal to B1 plus B2. But the thing is, B1, suppose I am taking a bigger B1, bigger than A1. In a sense, the column space of B1 is greater than the column space of A1. Similarly, you take a bigger B2, bigger than A2, then you take this ICM, you will find that A1, B1 bar D into A1, that cross product. You take the cross product with A1, A2, C and B1 bar D, B2 bar D and D bar. If you do that cross product as we did earlier, again this becomes 0. Each cross product becomes 0. Why I'm telling
the value addition of this?
Huh?
What will be the value addition? That previous slides told us. It is extended as that. It is just a property you observed, or you will make use of in your algorithm?
I will make use of it. Now, what is a section? You say if you write A equal to A1 plus A2, where A1 and A2 are disjoint, then each A1 and A2 are called sections of A. That is what I call section. This is has connection with the partial ordering and all that, minus partial ordering. If you have studied that, it has connection with that. But then this specific definition I give because it is more convenient for dealing with many results and it becomes a building block. So A1, A2 are sections of A. Now the theorem says if range of E is contained in range of A, range of F is contained in range of A transpose. That is F transpose, the row space is contained in the row space of A. Then this E F transpose A minus that expression is a section of A. See, the question is A1 is a section, right? Now, given a matrix A, and I am given two matrices E and F, the ranges are given. I have to find out a section of A with these ranges. Now, this is a section, but this section, the range of this section need not be range of E completely. There are conditions for that. So the range of this E, F transpose A minus E, reflex inverse F transpose, the range of it will be contained in range of E. The row space of this will be contained in the row space of F transpose. Its range will not be equal to E. There are conditions for being equal. Then this next theorem is one important theorem. It was shown by Anderson that if you take a positive semi-definite matrix V and another matrix X, how to find the intersection of range of V and range of x. Intersection of range of V and range of x. So this formula gives the intersection of range of V and range of x. Now, Anderson did not give this formula. And this formula we find it hidden in Rao's IBM, inverse partition matrix. So when he takes the G inverse of that partition matrix, so those blocks, you see, when he used what are those blocks. So in that, you will find this expression hidden. He has not given directly, but this expression is hidden there. So this gives the formula for getting the intersection of V and range of V and range of X, right? And now we are going to have this rotation, that is Vx. Vx is that the range of Vx is the intersection. The intersection we are talking about. So the range of Vx is the intersection, and if you take Vx bar as V minus Vx, that is the part of V. The part of V which intersects with the X is Vx. The part of V where X is not there is Vx bar. So now the Vx and the Vx bar are disjoint, and V is equal to Vx plus Vx bar. So I have split V into two parts. One is, the first part is that contains X. The other part which doesn't contain X. Now let us come to GGM. This is our GGM. Now what I am going to do is, in this variance covariance matrix G, I am splitting with respect to X. As I showed, V is equal to Vx plus Vx bar. And then now I am splitting G into Gx plus Gx bar. Disjoint matrices. And I am going to now introduce V, not that V. This new V, Gx plus Gx bar plus Xx transpose G bar. Now we are familiar with this rotation. And I put the matrix and then the subscript to something, you know the meaning of it. That is, Xx transpose G bar is the matrix which such that range of Xx transpose intersection range of G bar. G bar means not, which is not in G. Whichever is not in G. So that part of it in Xx transpose is given by that. So now I am defining V like that, and V plus C. C is the complement of V. Now V plus C is non-singular. I take the inverse, you get this. V plus inverse is that. Now V plus C whole inverse and V plus C is identity matrix. So V plus C and V plus C inverse, if you multiply, these two, if you multiply, the corresponding part that will remain, but the cross products will vanish. I've seen in IC method the cross products vanish. Therefore, you will have the product as this and multiply by y. The product of these two is I, multiply it by y, and take this expression, you will get this. So y is this, and this CC bar, y will be 0. This is a complement C, because y takes value in the range of G and X. It doesn't, outside it doesn't take any value. Now the C, where is C? In V, you see, only this much is concerned with the Y. Y takes only in the range of these three matrices. The C is a complement of this, means C doesn't contain Y. Therefore, the C bar Y, that will be 0. Now anyhow, I write these expressions as first part is y1, second one is y2, y3, and y4. So this is the decomposition of y. Now I have decomposed y into four components: y1, y2, y3, y4. And you can check this y1, y2, y3, y4 are uncorrelated. They are uncorrelated random variables. And the y4 is simply 0, as I already mentioned. Y4 is equal to 0. And y3, see this part,
But what will be the interpretation?
What?
What will be the interpretation?
I'm going to use this for my analysis, for the GGM analysis.
So you have that generated new variables.
I'm
Y2, Y3, Y4.
yes.
So now how will
See, y is now decomposed into four components.
that's understood. You have got four polygons.
And this y1, y2, it has meaning. It has meaning in the GGM analysis. Why I'm doing this? So this part y3 is simply a constant. It is a degenerate random variable. So this we can write as the first component as gx v minus y instead of this. That you can find from ICM method. So rewriting this, you can represent these components like this. Ways are uncorrelated. Y1 plus y3 contains complete information on x. The answer to your question. So y1 plus y3 contains complete information on x beta. Y2 is the error component with the variance sigma square g x bar. This is the error, and this we can just remove it. It has no use for us for estimating beta. So now I can just I can remove. I can concentrate only on the other components. Earlier, we was having that where it is, how to get the beta, where it is lying. Now I have located beta. I have confined myself to beta area. The remaining I remove. Now the y2 I can remove. Now y3, because of this, y3 is a constant v, vector v. It is simply a degenerate random variable. Now y takes the values in the affine space v plus range of g. V plus some point in range of g. Combine will get g. Y. Now similarly, as is decomposed g or v, we can decompose x also like this. We can decompose x in this manner, and we can decompose similarly when you multiply x with the beta, x beta will be like this. So x beta is what? Gx bar x beta plus v. You see, x beta is gx bar x beta plus v. So when beta varies, it cannot freely vary. It varies in such a way that x beta point is only this. Take v, definitely we have to take v. Otherwise, if x beta varies freely means you can take any point in the range of x. But here you see the condition is x beta should contain v. V plus some point in range of x, gx. So x beta is confined to range of gx plus v. So there is a restriction. Beta cannot freely vary. Otherwise, why should I fix v? You can take anything. Now it is restricted. So beta is restricted to have v plus something, range of that. Therefore, suppose I am going to test a hypothesis say x beta is equal to psi. X beta is equal to psi. That means I cannot take psi such that psi is any point in range of x. I cannot take psi lying any point in the range of x. I cannot take because of the restriction. Therefore, when you are asking me to test x beta is equal to psi, I will check whether this condition is satisfied. That is, when you want to check x beta equal to b, I will check whether b minus v I know. B minus v lies in the range of gx. If it doesn't lie in the range of gx, outright no, it's not a consistent hypothesis. I will not further do any computation. Straight away, it is wrong. I can do it. If it is right, then I will proceed. Oh, time over.
You have explained everything as a full paper.
Okay. So now IPM and just I will. Can you give me 2 minutes or fine? Let us see, compare IPM and our ICU. IPM is this. You take matrix B, P. G is our variance covariance matrix. X is the design matrix. So P is that. And P minus, suppose you represent like C1, C2 like this. And if you see linear static inference by Rao, he himself gives what is C1, what is C2, C3 and C4. Now in terms of our Gx bar, Vx, etc., we can write C1, whatever expression he has given, Rao has given, we can write in terms of our notation. Usually those components are nothing but this. So when range of x is not contained range of E as I told, it creates problem. Now I told you y can be decomposed into 4 components and y4 is 0, we can omit. y3 is sitting there. y3 is only a constant v. That we have seen. The y3 is only v. Therefore subtract this y3 from y. You take the remaining as a new model. If you take the new model, this problem is avoided, circumvented, finished. This is what Christensen has suggested. But then, yes, we take the suggestion, but then our approach further helps to tackle this place.
So did you try with some data? Did you try with some data?
No data, it is only theory. You can try it. Data definitely it will give.
So how because that most of the people.
The computer is there. Data it will give.
Because most of the people use factor analysis, they not use these methods.
No, when you deal with the data, there are other problems. There are further.
I say that if you have, they ask some students to develop some program and put it in that R programs and they can put it so that people use it.
Yes.
So that's the.
It can be done. Program can be developed definitely, and it definitely will work. Then representation of blue. See, Rao's the basic theorem is there. That is, Fy is blue of x beta if and only if f into x comma gx perpendicular. That is the confusing notation. Is equal to x0. That is Rao's basic theorem. And this theorem, from this, what is f? How to write f? What is the matrix f? So this research is going on, and there are several papers. There are several papers still going on. Now, what I say is, all those things can be simplified into one. What is f? This theorem gives the representation of f. So I told you in the IC method, the 2 parts, no? One is A1 plus A2, other is B1 plus B2. So that helps us to find this theorem. the representation proof of X beta is this projector. This is called a projector. The matrix multiplied by this G inverse called projector. So this projector plus this is a nuisance value. If you multiply by Y, these are 0. But then for theoretical purpose, we include it. For representation, theoretical representation, we include it, though this part is simply 0. So then the conditional estimator. So the VF, this Vx minus Vb minus, this can be broken into two parts further. Further, it can break it into uncorrelated random variables. And the condition H beta is equal to psi. Then the condition H beta is equal to psi. How to estimate lambda transpose X beta? This is the expression. Now we can. Now you find this result for the case of G is equal to I. For G is equal to identity matrix in Rao's book. One result is there for G is equal to I. And there he uses Lagrange multipliers. And there are several other papers. One paper gives for the general G, even singular G, a different circuitous method, again Lagrange multipliers. Our expression gives neat expression directly. Now regarding unified theory of least squares. Rao and Mitra, this linear statistic inference, Rao and Mitra's paper, that takes only, instead of G minus, it takes W minus, where W is equal to G plus X U X transpose. So only then we can minimize it and get the X beta, etc. But I say you take G, just straight away take G minus, you will get the result. So with this, I stop here. And there are scope for further research. Those who are interested in this, in ICM itself, now we have talked about square matrices. You can extend it for rectangular matrices. And this intersection theorem of Anderson with the formula which I wrote. So we can do it for rectangular matrices instead of PSD matrices. There are such problems. We can, people who are interested in it can continue to do further research. There is scope for it. Thank you.
So I think we have time for one short question or comment. Do we have any?
So I understand that your study on this, no, that it will be useful those who are using in the computation and all. And theorems are nice. I mean, today's date we find that students find it difficult to read Rao's book because they don't want to spend much time. Are you aware of any book who has simplified this one? Rao's.
This is my.
Yeah, this.
Yes, I think. To the author's knowledge, this is the new result.
New result. Okay, so you're comparing with that. So theoretically, it is beautiful. So that perhaps you have to see that how it is useful in the practical. This
definitely it will be useful for any model, modified GGM, everything. You can apply this even for variance component analysis. Instead of min-q model, you can use this method.
So
there is good scope.
It has to be solved properly. Otherwise, that proof is not difficult. So you have nicely explained. Okay.
Yeah. Okay. So let us thank again. So let us move to the final talk in this session. So our third speaker will be Dr. Iwsmga Johnson from NIT Karnataka, Surathkal. And the title of the talk is going to be Unbounded Closable Operators in Hilbert Spaces. And now I will give you a short introduction to Dr. Johnson. So It gives me great pleasure to introduce our distinguished speaker today, Dr. P. Sam Johnson. Dr. Johnson is a professor in the Department of Mathematical and Computational Sciences at the National Institute of Technology, Karnataka, Surat, India. His research focuses on functional analysis and operator theory. With 54 publications, 3 completed projects, 3 ongoing projects, and guidance to 8 PhD scholars, 4 ongoing, he has received merit scholarships, university second rank in MPhil, net qualification, and junior research. Junior Research Fellowship. He currently serves as the head of the department since 2023, former Associate Dean for Faculty Welfare and Associate NCC Officer, Captain rank. Please join me in welcoming Dr. P. Sam Johnson. Over to you, sir.
What is the ICC officer's captain rank?
I'm an NCC officer. So basically, I went for a training of 3 months. So in many institutions, NCC is running. So
you are in captain rank?
I am in captain rank. So it's just an honorary rank. Basically, I am a faculty. Yes, thank you. Good afternoon to one and all. So first of all, I'd like to thank Professor Manjunath Prasad for giving me this opportunity to present our work. And also, I'd like to thank the chairperson for giving an introduction. So the title of the talk is Unbounded Closable Operators in Hilbert Spaces. So the talk has 2 parts. In the first part, I would like to present some basic results in closed and closable operators. And the second part, I would like to share some of our work we have done recently in the last 1 or 2 years. So kindly excuse me, I will not be presenting any particular result and giving proof. I can give an overview of the results what we have done in 3-4 notions. So before getting into, so let us discuss the notions which will be used in this presentation. So throughout in the discussion, I'll be considering only Hilbert spaces, H and K, but still problems are open for 1H space settings. So if somebody is interested to work on, then they can think about the whatever problems we are going to see in 1H space settings wherever possible. So throughout in the discussion, I'm considering only linear operators. So I will not be telling every time linear operator. So all of my operators are linear. And the set of all bounded linear operators from Hilbert space H to K is denoted by B of HK. Therefore, bounded operators are nice enough. So you must have many PG students are there in basic function analysis course. They must have studied the properties of bounded linear operators. So for the bounded linear operators, it is characterized by the continuity. Therefore, as the map is linear, therefore, in order to check whether the map sends bounded sets to bounded sets, it is enough to check the continuity at a point. If it is continuous at a point, then it is continuous everywhere. But what do you mean by unbounded operator, which means that it is nowhere continuous. We can't expect the continuity at any point. So therefore, in the presentation, we will be discussing only the class of unbounded operators. And in the class of unbounded operators, one particular class is very well studied, and which is nothing but the class of closed operators. So class of closed operators is denoted by C of HK. So Professor Kulkarni, Professor Tambanayar, Professor Ramesh, and even Professor Kurmaya have done a lot of works in unbounded operator theory results in Hilbert spaces. So this space is denoted by C of HK. And then the advantage of a bounded linear operator, we don't need to explicitly tell its domain. So without loss of generality, we can assume that the operator has a full domain. So, but this restriction is required for unbounded operator. For a bounded operator, if it is defined on some domain subspace, then it can be extended to its closure uniquely. And as every closed subspace in the Hilbert space is complemented, we have an ortho-complemented subspace. Over the subspace, a map can be defined to be 0. Therefore, we can define, we can extend any bounded linear operator from a subspace to the whole space. Therefore, domain of T is not necessary to be mentioned for a bounded operator. Whereas for an unbounded operator, domains play an important role. So if you know the basic simple example of an operator which is a differential operator, so if I want to talk about on the space of continuous functions on 0, 1, then I'm expecting that the derivative should also be continuous. Therefore, we can't discuss on C of 0, 1 because differentiable, the function should be differentiable. Therefore, we go for the space of all continuously differentiable functions. So differentiable derivative and the derivative is continuous. Therefore, such restriction is necessary. That makes a little difference with the bounded settings to unbounded settings. And for any subspace, for any operator, so we have two subspaces. One is null space and range of T, range space. And then for a bounded operator, the null space is always closed. But for as an unbounded operator, the null space is not necessarily closed. So this is another basic difference with respect to the unbounded operator. And range of T is denoted by R of T. So range of T is a subspace, but it is not necessarily closed. But once range of T is closed by, if the is 1, 1, then by using bounded inverse theorem, we can expect the inverse operator which is also bounded. Therefore, in some places we require the closed ranges of the operator. In some places it is not necessary. So for example, if you consider a bounded operator, if you want to discuss about the existence of Morse-Penrose inverse for an operator. So Morse-Penrose inverse exists for any bounded operator, but the Morse-Penrose inverse need not be bounded. In order to have a bounded Morse-Penrose inverse, you have to have an assumption on the range has to be closed. And then the adjoint of T is denoted by T star. In a bounded settings for any operator, adjoint exists and which is unique, and then norm of the operator and its adjoints are same. But for an unbounded operator, to talk about existence of adjoints, so the domain should be dense. The domain of the operator is dense, then only we can talk about the existence of adjoint operator. This is also an additional assumption we require when we have T star. And then Morse-Penrose inverse of T, just now I said, so for any matrix, you know, Morse-Penrose inverse exists, but the same concept is extended for bounded operator, and same thing is extended for any other operators. So now this discussion that results for the Morse-Penrose inverse of a special class of closed operators called closed operators is very well studied, but we are going to discuss the same thing for closable operator. And then for any operator T, we have two positive operators T star T and T star. And if I have a square root of T star, positive square root, then that is denoted by modulus of T. And then we can compare the two operators with respect to this relation, which is called S is a restriction of T or T is an extension of S. This is a difference in with respect to unbounded operator settings. So because domains are different. So if I say S is a restriction of T, then domain of S is a subspace of domain of T. And then on the smaller domain, these two operators are same. Therefore, sometimes these are playing a very important role because we do not have an equality because domains are different. So let me start with the simple definition of a closed operator. So we consider a linear operator, the linear operator is said to be closed. So we consider the Cartesian product of the two Hilbert spaces H and K, and we collect all x, Tx and x is varying over domain. As the map is linear, this is a subspace. So when this subspace is closed, this is called graph of T. Graph of T is closed, then the operator is called closed operator. And with respect to the norm, we have taken a 2 norm, but you can consider any other norm because all of them are equivalent. For the practical convenience, this 2 norm is taken. So closed operator, it's a operator which may be unbounded. So by using the closed graph theorem, every bounded operator with a domain which is closed, then it is closed operator. So don't think that every bounded operator is closed. So that is not true. But if you have a bounded operator with a closed domain, then it must be closed. Therefore, closed and bounded are same when you have a domain which is complete. And sometimes we need to restrict the operator because we would like to sometimes we would like to make the operator to be injective by restricting its domain. So when we restrict to the null space of the orthogonal complement of null space of T, then we can expect the map is injective. But as we are discussing with respect to domain of T, therefore the carrier of T is nothing but the intersection of domain of T and the null space of T transpose. This is called carrier of T. So this plays an important role. So what is the definition of closable operator? Closable operator is an operator which has a closed extension. So if I want to say in terms of graph, if I take the graph of T, it's not a closed subspace. But if I take the closure of the graph of T, if suppose this is equal to closure of the graph of some other operator S, then we can say this T is closable. So there could be several extensions, among which we are taking the minimal extension, which is denoted by T bar. So that is called the closure of T. So what is the definition of closable is an operator which has a closed extension. Therefore, it is closable. And every bounded operator is closable because when we have a domain of T, when we talk about domain of T bar, it is same as domain of T bar. So therefore, every bounded operator is closable. And then every closed operator is closable because that operator itself is closed. We don't need to look for any other extension. The smallest extension itself, the operator. Therefore, we have a big class of operators which is called closable operators. It contains all the bounded operators and closed operators. So this particular class of bounded operators is not very well studied. Therefore, we tried in finding some basic results in this class. So that's what I'm going to present a few results. So this is a simple example. So beyond closable, there are operators. So this is a simple example which tells about there are operators which are not closable. So we take a dense subspace, here denseness is not necessary. So when we talk about the adjoint of T, then denseness is required. Without denseness, this is true. So we choose a non-zero element in the domain. And then we consider an unbounded linear functional on D, and the map is defined. So which is a finite rank map. So f of x is equal to f of x into x. So x naught. The x naught is fixed. So with respect to this, you can look at this operator is not closable. So there is another characterization to check whether the operator is closable or not. If we choose any null sequence xn, which means xn converges to x, if txn converges to some other element, then y has to be 0. So in this case, this is not going to happen. Therefore, this is not a closable operator. And there is another observation. Even if you look at the domain of T star, because D is taken to be dense, T star exists, the adjoint exists, and then domain of T star is an orthogonal complement of x naught, but T star is 0. So on the full domain, the T star is simply 0. So therefore, this is interesting when you consider an unbounded operator. So this is another example of a class of operators which are not closed, but each operator is closable. So we consider the domain of Tk is a space of all k continuously differentiable linear operator. And if you assume the condition, the function on A and B taking 0, then this is the domain and the map is nothing but the differential operator. So in the differential operator, if you look at it, Tk of f is equal to minus IF. Minus I is not necessary for discussion, but in order to have the Schrodinger equation, so this is typically taken in all the textbooks. With respect to this domain and the operator we define, then we have a collection of operators. So none of them is closed. And then we can say T1 is bigger. When we go from 1 to 2, number is increasing, automatically domain becomes smaller, and then we can have the corresponding restrictions and extension, everything. And then each Tk is closable. But one good thing is, if each Tk is closable, then what is the closure of one operator? So the closable of all operators are same. The closable of all operators are same. What is an operator? The operator is same, but you have a domain difference. If you look at the domain of Tk and domain of T bar, so T bar is a closed extension of Tk, but if you look at this domain of Tk, which is bigger, so therefore all absolutely continuous function, which is a weaker notion than the continuity, and then stronger notion than this Lipschitz continuous, all absolutely continuous functions and the derivative of that function in L2 of AB. Therefore, there are plenty of operators which are not closed but closable. So this is a notion which is used for closed operator. So you can find the proof in the Goldberg book. And for a closed operator, an operator is said to be lower semi-bounded, then this inequality is true for all x in C of t, the carrier of t. So if such gamma exists, then we take supremum of this gamma, then the number which is called reduced minimum modulus, which is called gamma of t. This gamma of t is a number which characterizes the topological property of the range. So therefore, the next theorem tells, in order to check whether the range is closed or not, so it is enough to find gamma of t and test whether it is positive or 0. So if it is positive, then the range has to be closed. So we use these results to prove or to test whether an operator has a closed range or not. And this is a standard Moore-Penrose inverse. As I said in the beginning, Moore-Penrose inverse exists for any class, but we don't need to expect it has to have a full domain. If I have an operator which is closed, then I can define T dagger from range of T and orthogonal direct sum of range of T per. But remember, this range of T and range of T per, the orthogonal direct sum is not necessarily the full space because range of T is not closed. But this is some dense subspace. But if you have an assumption on range of T is closed, then T dagger is bounded. So T dagger is defined like this. Then we restrict the T to the carrier of T. Then the map becomes injective. Then we can take the inverse of T. That way we can define T dagger Y. But the same thing one can also define for any operator, provided you have a nice structure in the domain is said to be decomposable domain. So what do you mean by decomposable domain? The domain of the operator is the sum of the orthogonal direct sum of the null space of the operator and the carrier of T. If this is possible, then we can discuss the Moore-Penrose inverse of any operator. So therefore, for a closable operator, we have assumed this domain has a special property, which is a decomposable domain. Then we define the Moore-Penrose inverse and discuss the properties related to that. So this is the first notion, which is Iwsmga stability. So when people are working in differential equations and trying to solve operator equation, they may not get the exact solution in one go. So they may get an approximate solution. That's what the Iwsmga stability to say this, whether the particular operator equation is stable or not. In this, stability has different notions, but with respect to Iwsmga stability, so we are discussing some number which talks about the stability of the operator equation. So we choose any y in the range of A. So we are having an approximate solution of the operator equation Tx is equal to y. Then the question is, can we find an exact solution around x? Because x is an approximate, can we find an exact solution around x? It is possible if the constant is known to us. The constant is called Iwsmga stability constant. If the constant is k, then we can find the exact solution in the k epsilon neighborhood of x. So therefore, this k is very much helpful to search the exact solution of the operator equation when we start with the approximate solution. So all three are equivalent because we have considered a linear map. Therefore, this is a simple notion you have. When you have a Iwsmga stability constant, anything more than that is also Iwsmga stability constant. But we are looking for a ball which is smaller so that we can find out the exact solution in the epsilon neighborhood of k epsilon neighborhood of x. Therefore, infimum of the Iwsmga stability constant is not a Iwsmga stability constant in general. If the null space of A is proximal, so proximal you have any point in the space, this is a subspace. So for any point you can find a point on the subspace. The distance between the two elements is the same as the distance between the element and the set. So if that happens, then the set is called proximal. So the proximality tells the infimum of all Iwsmga stability constant, again a stability constant. And this is a characterization given by Kisarova in 2006, and he has characterized in terms of the range, the boundedness and lower semi-boundedness. So the corresponding Iwsmga stability constant, that infimum of all, which is nothing but the inverse of the minimum modulus of T. Therefore, if somebody knows the infimum of the minimum modulus of T, then we can easily find the gamma of T because we know the range of T is closed. So this is a characterization for a closed operator. And this is a simple example which talks about an operator can be Iwsmga stable but the inverse is not Haslam stable. So this example on the sequence space, this is a typical diagonal operator. The diagonal entries are 1, 2, 3. This is an unbounded operator. So this operator is onto, therefore it is Haslam stable. But when you discuss about its inverse exists, but which is also bounded, but the range of T inverse is not closed. Therefore, it is not Haslam stable. And in the closable operators, we discussed the Haslam stability constants of the operator and its closure, T and T bar. So we found that the Haslam stability for the closure of T is smaller than the Haslam stability of T. So this is for a closable operator if we start with the Haslam stability on T. But we do not have a characterization. What we have seen given by Isarova is not true for closable operator. But with this, for the operator which has an extension, this is true. And then if we want to analyze certain special type of operators, so in theorem 13, we have an operator I plus T star T bar. And the next slide, we have T times I plus T star T bar. So this type of operators are playing very important role in applications. So we have checked the Haslam stability of such operators. So here we are saying that if this particular operator, theorem number 13, this particular operator is Haslam stable, then the operator must be closed. This is a necessary and sufficient condition. We cannot get anything else new. And theorem 14 says that we have an operator T bar I plus T star T bar. So we can discuss the Haslam stability. So just we have an assumption on Haslam stability of T, that is enough. And then we discuss about some spectral properties of this operators. So therefore the spectrum of the operator given by T star T bar restricted to the null space, it doesn't contain 0. It is on the real line. So therefore this is an extra conditions, extra results we have got when we have an assumption on Haslam stability. So these results got published in the journal Mathematics Next Fiction. So next notion, which is a Moore-Penrose inverse of an operator. Already I have given a brief introduction about the Moore-Penrose inverse. So there are few results about the Moore-Penrose inverse. These results you can find in the book Ben Israel and Riveri for densely defined closed operators. But if you look at the statements, the inequality is 5, 7, 8. But we can't expect the same inclusion, the equality relations for the closable operators. Because for a closed operator, T and T bar are same. T is equal to T bar, but for a closable operator, they are not necessarily same. So this is a set of results we have proved in a paper. For a closable operator without any additional assumption on T, and the T dagger is always closable, and then the closure of T dagger is a restriction of the Moore-Penrose inverse of closure of T. So we can't have an equality symbol. And then as I said earlier, so if you look at number 3, so we have seen for a closed operator, T is equal to T double dagger. So when you find the inverse of a matrix twice, you can come back to the same matrix. But for the case of closable operator, this T double dagger lies between T and T bar, because they are not same. T and T bar are not same. But we can also derive the earlier results from this, because we know T and T dagger are same. So when T is equal to T dagger, we get all the previous results. And then if you look at the results 4 and 5, we do not have a proper equalities. So the inclusion relations are there comparing the two set of notions. So the inclusion relations are telling the maximum domain what we have. So we may not go beyond that. Therefore, when we say an operator is a restriction of another operator, this operator has a smaller domain. Therefore, we can't discuss anything beyond that. On the smaller domain, these two operators are same. So therefore, we have to be careful when we have this inclusion relations. And there are some simple results with respect to the Moore-Penrose inverse of the direct sum, and then corresponding the minimum modulus of the direct sum of two operators. And then same thing is done with respect to the modulus of the operator, the direct sum of operators. And so this results, and then the direct sum of closed operators are there in this journal, linear and multilinear. And this is the second set of works. The third notion is nothing but EP matrix. So you are aware that EP stands for equal projection matrix. The operator, the matrix and its transpose or A star conjugate transpose are same. The ranges are same. The column space and row spaces are same. And the matrix is called equal projection matrix. And the equivalent characterization is the matrix commutes with its dagger. And this notion was extended to bounded operator by Campbell and Mayer in 1975. And then this concept was same thing, same assumptions. The range of T to be closed. And then if you have range of T and range of T star are same, then the operator is said to be EP. When you have this inclusion relation, then we say is a hypo-EP operator. And throughout the discussion, so now this notion and next notion, so we are considering only closed operator, which is a special class of closable operators, densely defined. And an EP operator is not necessarily true. Yeah, yes, thank you. So the T may not compute with T dagger on the entire domain because T dagger may have a, so on the domain of T, these two are same. So this observation on this. And then we have also discussed the sum product of EP and hypo-EP operators in this settings. And then we can also perturb this type of operator with something else. We have an EP operator. If I'm perturbing this operator with another class of operator, whether the sum will remain in the same class. So how much this operator can be perturbed. So that is also analyzed in this work. And then we have also done with respect to the composition. And then the spectral radius and the minimum modulus of T are compared for an EP operator. So this got accepted in operators and matrices journal. And this is the last final notion, which is a generalized Cauchy dual. And generalized Cauchy dual is done for here in this through discussion. Sometimes we may require the closed range of T, but T is densely defined closed operator. So we define the generalized Cauchy dual instead of replacing the regular inverse by Morse-Penrose inverse. And this is an operator. But if this operator, the T, is an operator with a closed range, then the corresponding, the generalized Cauchy dual is nothing but T dagger whole star, which is bounded always. Therefore, we have a simple expression when we have an additional assumption on T. And then when we find the composition or double 2 times of generalized dual of the same operator, can we get back the same or not? It is not generally true, but it is closable. The corresponding closure is T. And then we can also find the product of two, composition of two, the composition of two generalized Cauchy dual operators with respect to the generalized Cauchy dual of the compositions. So that is done here. And then we have taken many special class of operators, self-adjoint operators, normal operators, quasi-normal operators. So we discussed all these results for those collection of operators. So this got accepted in the Siege mathematics, Act of Mathematics here, Siege. So these are the publications in this direction. So I would like to tell you that very few people are working in this direction. And Professor Motard from University of, is from Algeria. Very few mathematicians are working in this domain. And then we have also tried the same thing with some other spaces, semi-Hilbertian spaces, but it did not go well. But we understand that on the classical settings, either in Hilbert spaces or Banach spaces, these problems are addressed, which may be useful for people who are working in quantum mechanics and other areas. But we did not work in any applications. So we have done only theoretical work. So these are the references. So you are aware that the Ben Israel book is a very good book for generalized inverses. And then you have a very good book written by Goldberg for unbounded linear operators. And Hizarova and Mayura discuss about Hesbaum stability of densely defined operators. And then the Pearl characterized the EP matrix, saying that the matrix is commuting with its Morse-Penrose inverse, then it is EP. And then the Conant, the book Unbounded Self-Adjoint Operators on Hilbert Spaces, that's a very good book for unbounded operators. And Shimorin, he defined while discussing the wandering subspaces of operators. So he introduced a notion of the generalized Cauchy dual. So we extended. So this notion was basically defined by Shirimori. Yes. So with this, I would like to stop.
Thank you very much. So do we have any questions or comments, the audience?
I wish I was scared to ask a question. Now I don't know.
Yes.
We had a very inspiring lectures by V.S. Varadarajan in my day. And he used to teach us spectral theorem for bounded, spectral theorem in the Hilbert space. Then it continued with unbounded operators, ID by dx.
Yes.
Okay. And then the function which you wrote, I plus tt star inverse, whatever it is.
Yes.
I didn't understand at that time. And in fact, not Varadarajan, I had a classmate who said the whole idea is the infinity, the zero, open, and close zero, open infinity. And then all you try to do is to make it into a compact set by coming around it.
Yes, sir.
And that notion helps you to recover the spectrum from the point spectrum kind, from the bounded operators thing.
Yes.
And those were really beautiful lectures in those days.
Wow.
And you are kind of reminding me of them.
Okay.
Nice. Nice to hear it once again. Thank you.
Suppose T is closable operator.
Yes.
T dagger unique, but closable operator. Suppose T is a bounded linear operator, then T dagger is unique.
Yes.
Even for T depend on densely defined domain, also T dagger is unique. Similarly, suppose that T is closable operator. Is T dagger unique?
T dagger is unique because we have assumed the operator has a decomposable domain. So with respect to the decomposable domain, so domain of T, which is decomposed as the sum of the orthogonal carrier of T and its the orthogonal complement of null space of N. So with respect to this decomposable domain, so we are getting the typical structure of the defining the Morph-Pintos inverse. So it is unique. Unique, yes.
So did you try anything about group inverse in this direction? I mean, so like Morph-Pintos inverse, group inverse of an operator is there?
No, sir, I have no idea. Yes, I don't know.
Fine, thank you.
Okay, so I think it is time for us to close this session. So let us thank Dr. Johnson again.
I thank Professor Mika Matila for chairing the session. So now we'll break for lunch, and the next session starts at 2:15, starting from talk by Raghavan sir. Thank you all.
Thank you.
You see, even the original patent, I can find the close field for which this computer solution actually the solution is. Then say yes, okay, acceptable. So your definition of the material epsilon is very similar. Very similar. Yes, very similar. So all these ideas first can go through the methods, correct. And then try to slowly push. Yes. Similar thing, I tried to do as a in those days. I tried to extend the term of preventive. Okay. To instead of corn, I assume it's a complex set. Okay. Right. Then try to prove whether in a complex set in balance. When the transformation is everything very whether we can find positive eigenvectors, and then eigenvectors something like that. Those were inspiration from
many good results are there for phone.
Yes.
But if they are extended to convex setting, then it is very useful.
All very factor there is less than one. Rather than one. Oh, I have equal to one.
I'm sorry. I find that. Thank you, sir. Thank you, sir. Thank you for inviting me.
Talk on scaling of. Load fund. I want you to deliver this.
It's okay.
I want to. I want to. Your own lab. I can use my own lab. You have to share this slide.
That's what I changed the topic because they can't do anything else.
Or you can give the. So I don't have, I have it only there. So, okay. That's why. What do you mean? You give the connection.
Yes, is it okay if I take the PDF and share in my computer?
Yeah, editing, you can do whatever.
I just show.
Okay, but I'll make a note. Thank you. Okay, thank you. Hi, sir.
I'm Rafi from Kerala.
Oh, very good. Thanks. Thank you.
Actually, I started my.
This one, this one. Okay. Yeah. Yeah. Ask my son to help me go and think about it. But there is no white vector. No. You said many of mine. Wi-Fi. 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 No, without Wi-Fi. Okay. I don't know much about Iclaa. Is it okay? You can go anything over. Okay. Yeah, that one. Okay. Professor is waiting for you. Yeah, yeah. Yes, really? Okay. And yeah. This is the, this to relieve. Yeah. Yeah, yeah, sure. Yeah. Okay, my gosh. We'll go. The technology is so advanced now. Yeah. I know nothing. Yeah. That's why I also in the morning, morning, I call my son. Oh, listen, so sometimes he directly handles. Yeah. Maybe can I leave it here? Otherwise, carrying it. Yeah, yeah. You can leave it from there. Yeah. But you don't need anything, right? Huh? You don't need anything. No, I get it. So I. Hmm?
ನಾವು ಕೆಲಸ ಮಾಡೋಣ ಅಲ್ಲ ನೀವು ಲ್ಯಾಪ್ಟಾಪ್ ಅಲ್ಲಿ ಓಪನ್ ಮಾಡಿ ಕೊಡಿ ಅಂತದ್ದು ಇದಕ್ಕೆ ಏನಾಗ್ತದೆ ಅಲ್ಲ ಅದೇ ಈಗ ಅದ್ ಮಾಡೋದಾದ್ರೆ ಡೈರೆಕ್ಟ್ ಅದನ್ನ ನಲ್ಲ ಇದಕ್ಕೆ ನಂಗೆ ಒಂದು ಆಡಿಲ್ಲ ಅವರು ಯಾರ್ಯಾರು immediate change. ಹೇಗಿದೆಯಾ ಕತೆ ಇಲ್ಲ
ಮೊಬೈಲ್
ಆಫ್ ಮಾಡೋ ಚಾನ್ಸಸ್ ಎಲ್ಲ ತುಂಬ ಉಂಟು ಟೆಕ್ನಾಲಜಿ ಗೊತ್ತಿಲ್ಲ.
ಇವ್ರಿಗೆ ಹೇಳ್ಬೇಕು ನಾಳೆ ಅದು ರಿಮೆಂಬರಿಂಗ್ ಲೆಜರ್ ಎಕ್ಸ್ಟ್ರಾಕ್ಷನ್ ಅವೆಲ್ಲ ಮಾಡಬೇಕು. ಆಮೇಲೆ ಈ ಸ್ಟೇಜ್ ಅಂತ ಹುಡುಗಿ ಮಾಡ್ತಾರೆ ಅದು ಫಸ್ಟ್
ಹಲೋ 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 ಹಲೋ. ಶ್ರೀನಾಥ್ ಸರ್ ಕೇಳ್ತದಲ್ಲ?
ಆದ್ರೆ ನಾಳೆ
ಹಾ
ಪರ್ಸನ್ ಇರೋದು SKG ಇರ್ತಾರೆ. ಅವರು ಇವ್ರನ್ನೆಲ್ಲ ಮಾಡಿದ
After will be very difficult. You want but just scaling problems in the applications. Here. Last one. One paratha.
Boarding time is high. Yeah. நாளைக்கு என்ன நாளைக்கு 1 மணிக்கு நைட்டு 1 மணி ஏற்று ஃப்ளைட்டு 9:30 தான் எனக்கு நைட்டு 9:30 இல்ல சரிதான் வருவீங்க ஒரு
We'll wait for 1 minute. Yeah, it's going to yeah.
So welcome everybody to the post-lunch session. So this session is chaired by Professor Stephen Iclaa. Over to you, sir.
Good afternoon, everyone. Welcome to our afternoon session. It's a pleasure for me to introduce Dr. T.E.S. Raghavan. He earned a PhD from ISI Calcutta in 1968 under the leadership of the mighty C.R. Rao. Since then, he's gone on to an illustrious career at the Department of Mathematics, Statistics, and Computer Science at the University of Illinois, Chicago. He's now a professor emeritus. His research focuses on game theory, linear and nonlinear programming, matrix theory, applied statistics, and operations research. He has more than 60 papers, including works on zero-sum two-person games, stochastic games via policy improvement, non-negative matrices and applications, assignment games, and tax evasion models. He's made significant contributions to dynamic games and operations research throughout his career. And today he's going to tell us about scaling problems and their applications.
Thanks for the nice introduction. When Buffett came to join me as a graduate student, I was interested in pushing him towards game theory. But soon he explained to me that he is more interested not in analysis side, but more in combinatorics. He explained explicitly. And one of the problems which appealed to both of us was on scaling of matrices. In a sense, I am more interested in starting with a problem which is physical, which takes you to mathematical question. So various biological, statistical, and social science data come in the form of cross-classified counts tables called contingency tables. Scaling the cell entries of such multidimensional matrices involves both statistically well-posed as well as mathematically well-posed problems. I would like to first describe several situations where scaling can be useful. We then prove a general theorem that demonstrates the existence of a scaling factors. We also describe a natural scaling algorithm in the problem of scaling non-negative matrices to obtain prescribed row and column sums. In order to study the convergence properties of the algorithm, it's convenient to work in Hilbert's projective metric, but we will not get into it. In the last section, we consider the problem of maximum likelihood estimation in contingency tables. This area of statistics, which forms part of discrete multivariate statistical analysis, is of considerable interest to researchers at present. Assume that Army, Air Force, Navy, they have people, technical, non-technical, and research persons. So the numbers indicate the current situation. Next year, the government decides to change it. They say that Air Force should have a budget, higher budget than what they have, like that they have a different increase of budget, and similarly, they have stipulation on how many technical people should be there or how much should be spent on them and non-technical and research. That is matrix B. Matrix A says what it is. Matrix B imagines what the government would like it to be. The government basically only stipulates the row sums and column sums. It doesn't put any more conditions. Okay? So, what should be the plan? For example, here is one plan, Air Force. Remove all technical people. Non-technical people keep 320, research 80. So when you look at the matrix below, it satisfies all the constraints which the government wanted. But that is nonsense. Nonsense means the human side of it is horrible. So we need to find a matrix that is somewhat closer to the original matrix in some form, meaningful form, in some suitable measure of distance. Take another example. We know a stochastic process, which is a stationary Markov chain, with finitely many states and a doubly stochastic transition matrix. The problem is to estimate the probabilities Pij based on observing the process for a finite time. The maximum likelihood estimates based on the observed data are quite hard to find. Roughly speaking, the ML estimates of the parameters or values of parameters which lead to the maximum probability of getting the current sample. For example, if the stationary Markov chain has 3 states and we had these observations for 18 days, so this matrix summarizes from state I to state J. But I made a mistake at one of the calculations. The last row should be 1, 1, 2. Okay. So there are 2 ways of thinking. What is the probability of moving from state I to state J? Pij, if you take the first row, when you average it, then that gives you half. But if I go along the column, assuming that the last row is 1, 1, 2, then it gives you a different estimate, which is 0.6. You have 2 different estimates for the same thing. which one to be used. Half of the time system moved from state 1 to 2, it is P12 is 0.5, the other one is P12 is 0.6. So since we basically scale the rows to arrive at one estimate and scale the columns to arrive at a second estimate, the heuristic approach would be to alternately scale rows and columns, and hopefully it will converge to what we want. So in general, we can ask a simple question. Given n by n matrix A with positive entries, can we find xi, yj positive such that the matrix C is doubly stochastic? C, which is aij, xi, yj. One more example in scaling in Gaussian elimination. Take the simple example, x1 plus 10,000, x2 is 10,000, half x1 plus half x2 is 1. If you used brutally the Gaussian elimination, one by one, x1 is 10,000 minus 10,000 x2, minus 4999.5 x2 is minus 4999, eliminating from the first one. But when we do this one, we also want accuracy. I don't want the accuracy beyond the first 3 decimals. If I use that one, you will notice that the solution will be x2 will be 1, x1 will be 0. Oh, what happened? Huh? My God. Is it coming? Yeah. Yeah, okay. Okay. The solution rounded to 3 decimals gives x2 1, x1 0. This is quite unsatisfactory even from the point of view of backward error analysis. What do you mean by that? You want to find another matrix which is close to the original matrix, for which this solution which you get is exact. And from backward error analysis also, you notice that it's useless. So fortunately, there is a way out. The key idea in practice is the individual rounding errors are less significant when the non-zero entries are roughly of the same magnitude. So such systems are called well-scaled systems. So it is possible to choose possible scale factors Ri and Sj such that summation Aij xj is Bi, and one solves for summation Aij Ri Yj Sj is Bi Ri, where we identify xj as Yj Sj. And then you can notice that with a correct choice of R1 as something, 10 power minus 4, R2 as 1, S1 as 1, S2 as 1 gives you it's quite good. Okay. But that doesn't mean any scale factor is going to be good. This particular scale factor happens to be good. There are many such examples. Okay. So the one important thing which I want to talk about is this problem was attacked in 2 different ways. First, Buffett worked in his PhD thesis on using the homotopy arguments. I was trying to do the same thing using duality theorem with the assumption that all the entries are positive. But later, more important is to allow zero entries into the system. And that's where we join together to make this paper work. Okay. For example, you take the matrix A as 0, 0, 1, etc. If you start alternately scaling it, it will never end. Basic reason, the matrix, the zero pattern of this is not consistent with the zero pattern of any doubly stochastic matrix. Okay. So this is again something gravity model. Forget about it. I will skip this. Okay. So everything is now under one single theorem. What is the theorem? Let K be a bounded non-empty polyhedron given by K equals all vectors in Rn that are non-negative, and for a fixed matrix C and fixed vector B non-zero, C pi equals B, and K is a non-empty bounded convex set, where C is an m by n matrix and B is a non-zero vector. What we are now assuming is, suppose Y is some element in K which is consistent with another element X non-negative in the zero coordinates. Suppose you are given, you know already there is a Y, you are given a vector X non-negative which has the same zero pattern as Y. The theorem is, we can find Zi positive, I equals 0, 1 to m, and a vector pi, an element pi in K, such that the jth coordinate of pi is the same thing as the jth coordinate of x, j, x, multiplied by pi Zi power Cij. Any pi of the above type is unique. So, to get a feeling for this theorem, let's take a simple example. Suppose A and B are two by 3 matrices with the non-negative entries and with the same zero pattern. Let the row sums be R1 and R2, column sums be C1, C2, C3 for the matrix B. B is the future matrix, A is the current matrix. Let K be the set of all non-negative matrices with the same row sums and column sums as B. A typical element of K is some such vector. So given the matrix C, I have written row 1 sum is 1, 1, 1 is R1, row 2 sum is R2, column sum 1 is C1, 2 is C2, 3, blah, blah. We have K equals Y, Y non-negative Cy. We can associate with each row, U1, U2, V1, V2, V3 that are positive. Okay. The given matrix A can be identified with the vector X, B with the vector Y, with Z as U1, U2, V1, V2, V3, such that for some pi belonging to K, we have pi 13 is A13, U1 power 1, U2 power 0, V1 power 0, V2 power 0, V3 power 1. So basically it means pi 13 is A13, U1, V3. The scaling comes this way. So a further extension of the same theorem is K is given like in theorem 1. Let phi be a point to set map K to 2 power K be a set map satisfying the following condition. For each X, phi x is a non-empty closed-bounded convex subset. The map phi is upper semi-continuous, which means xn tends to x and yn tends to y, and if yn belongs to phi of xn, then y must be in phi of x. So then for any y belonging to phi x, the jth coordinate of y is also 0. Then the theorem says you can, for any given u, you can find a z in K such that u belongs to phi of z. So this theorem extends Darroch and Ratcliffe's theorem by allowing 0 entries. First thing is, the key ingredients are continuous maps on polyhedra preserving 0 coordinates, extension to upper semi-continuous set-valued maps, and complementary slackness conditions. All of them put together gives you the answer. So first we have to construct a set-valued map where S is the unit, not the unit symbol, that's nonsense, something else. And show phi satisfies the conditions of Kroneker's theorem, and we use LP duality to extract the scale factors. So the first lemma is K, if it is bounded, and G, K to K is continuous with the property xi equals 0 implies GAX equals 0 for any x, then the map G maps K onto K. So the basic idea is to study the structure of the boundary of K. This boundary set of K we have to study. You can assume, without loss of generality, that there are at least 2 points in K. If there are at least 2 points, then it has a relative interior point. And then if you take a relative interior point and any boundary point, the line joining that is completely there, which satisfies every point other than the boundary point is a relative interior point. And that is the key to proving that every relative interior, every boundary point will have some coordinate 0. And if some coordinate is 0, then it is a boundary point. So that is the basic idea for the first part. Then the function g is also sending the boundary to boundary, and it acts as homotopic to the identity map, and therefore g is onto by Kroneker's theorem. Now the upper semi-continuity has to use the simplicial approximations. That part requires, just a minute, let me. Okay. What you do is you take your polytope and split it into smaller polytopes, which are simplexes. So let Pk be a fine mesh of simplicial partitions with first T belongs to Pk, then T is a simplex. For each K, the number of elements in Pk is finite. If two simplexes are intersecting, they should intersect only in a common face. That is the requirement for the simplicial partition. Either they are disjoint, or if they intersect in a common face. And if T belongs to this collection, and F is a face, that must be in the collection. And any 2 points in one of those simplexes, any such subsimplex you take, the distance between them can be made less than 1 over K for the kth simplicial partition. And if Xk is the collection of all vertices of the simplices, then you can make finer and finer partitions. It is very similar to the proof of Brouwer's fixed point theorem using Sperner's lemma in some sense. It's very similar. So that's the whole idea. And X1 contains all the extreme points of K. Such partitions are well known, and for each xk, choose any y belonging to phi x. You can choose an arbitrary y and define the single valued mapping fkx is y if x is this. Then you develop the simplicial approximation function x as summation lambda xik, where xik are the extreme points of each one of those simplices. And this function is well defined and is continuous on k. One has to check it very carefully. There are several steps in between. And that is the basic idea of that thing. So the one is the Kronecker index theorem, first round guarantees subjective. But the second one, upper semi-continuity, guarantees a covering. Okay. So with these two, even here there's a lot of technical careful check, which I don't think we can do any of them. I can only say that. Okay. Now I want to define the feasible set. What is a feasible set? Oh, no, I have to also say one more thing. Just a minute. Let me see. No. Okay, fine. So originally it was k equals some pi with c pi equals b blah blah. But I am now adding some more conditions. Namely, I consider only those points of k where whenever yj is 0, πj is 0. So you put the additional restriction, and that is our set S. That is the constraint set k restricted to the 0 pattern of y. Now I am constructing a function pjh, which is log of xj over hj. H is an element of S, of course. If xj is positive, hj must be positive because of the constant condition. And if xj is 0, h will automatically be 0, and therefore pjh is 0. And sometimes xj, which is arbitrary, can be positive, but hj can be 0, in which case we define it as log infinity. And we have the convention 0 log 0 is 0, 0 log infinity, blah, blah. So the next major step is to show that this map phi of h, which is p pi star, which is the minimum of p pi. Why should the minimum be? It's only infimum. It's bounded below, I have to show. So once I show that, then I have to also show that the minimum is attained because of the upper, this function phi is upper semi-continuous. So the phi h consists of all pi in S that minimize the objective function subject to these constraints. So the constraints are linear. The objective function is a linear function, and it has an optimal solution. Okay. This is all, forget about it. No, these are all, I'm just continuing with the proof, which I don't need. So, what is an optimal solution to minimize minimum of pi belonging to S of P star pi S minimum P star pi j, where P star j is P star P H star j. This is actually a linear programming problem because the objective function is linear. So it has by the duality theorem, you have an optimal solution to the dual. So an auxiliary to handle the zero patterns. So we have first Cij pi j is Bi, Cm plus 1. You introduce one more row, Cm plus 1, such that Cm plus 1 j pi j is 0, where Cm plus 1 j is equal to 1 or 0, depending on the other one is 0 or 1. That's how the complementary slackness is introduced. So the dual to this is maximum summation Bi Wi. And the complementary slackness will give the following. When Yj is positive, we have Cm plus 1j is 0. Therefore, we get Cij W star I is Pj star as log xj over hj star. Now you can take exponentials on both sides and that's what you get. And you can take exponential with the minus sign, you get that. So define Zi as that. So hj star is this. So we get the exact formula. So that is the main theorem. See, my son, I asked him to transfer part of it from one part and from the paper. So he goofed it. I am responsible, but he is not responsible. He only knows how to make it into. Otherwise, if they gave me a chance to write it, it would be easier for me. I'm more used to writing than this kind. Okay. Okay. Forget about all these things. The same thing comes 10 times. Okay. We described some heuristic improvements for scaling non-negative matrix with doubly stochastic pattern. Simply suppose you are given this matrix. First you arrange the row sum and then column sum, adjust it each time. The Synchron was the first person to prove that it converges to a doubly stochastic matrix. And repeating this up, but it takes centuries before you can reach the solution. Okay. Now, if I consider this matrix, in fact, I myself tried to do it with Excel. That's all the thing which I had at that time. It is not even Excel, it was something else. I have forgotten its name. After 500 approximations, it gave this number. This was the approximate to doubly stochastic matrix. There is significantly higher than in the previous example. Now, it is possible to improve convergence by choosing scale vectors appropriately. We present three intuitive algorithms. Their convergence can be proved, though comparative rates are typically evaluated via only simulation. So the first thing is, you simply consider the average of all the entries. Then something is too far away from the average. Suppose it happens to be, they say, first row 1 or row I, whatever it is. Then you forget about the first row. If suppose it is the first row, forget about the first row. Take the average over the rest of the rows. And that is considered closer to the true mean mu. So then all you do is you scale the first row to achieve this average. And now you update the columns and repeat this process. This is the first step. This is an intuitive step. The second method is you consider the maximum deviation between the row U and say column V. Column V is sums and row U sums. Take whichever is the maximum, let's call it as gamma U and CV. If this is small enough, we drop out. We say that this is all we can. Otherwise, you can take F, which is the ratio of half of that thing, and scale the row U and column V by this F. The third strategy is to mix the two things. That's all. That's all the thing which exists. At that time in the market, I don't know what is new. Now we move on to maximum likelihood estimation. The outcome of statistical survey is very often a final report in the form of a multidimensional matrix. So let's take an example. In a survey on car accidents, the response from 4,000 victims was summarized according to the type of accident and the severity of the accident. So what are the two kinds? The car was completely rolled down, or the car was not rolled, but still people had so many accidents, not severe, moderately severe, and severe. This form of reporting is called a 2x3 contingency table. The problem of statistical interest is to estimate the expected number of accidents in each category. But this survey itself could be of two different kinds. One is it reports 4,000 accidents from an unknown population. The second one may be it's based on a fixed sample of 4,000 victims. The first case we use the Poisson distribution, Xij to be the count in cell ij with mean lambda ij, and that is the format of the density format. The second model, because you are conditional, okay, so it will be the multinomial kind of distribution. So the maximum likelihood estimate basically says it is maximizing the best value of theta for a given data point x. So the data reduction can also be seen through sufficient statistics. So what are the sufficient statistics here? So if you find the sufficient statistics, you can forget about the rest. Okay. So in this problem, in our accident model, if suppose we assume that the accident has nothing to do whether it is rolled over or not, the way the different categories happen, it could have been due to rolled over or it could have been not due to rolled over. But if you assume it has no relationship to that, then the Pij can be simply some alpha beta j, and then we can the row sums, the row marginals and column marginals, they actually form the sufficient statistics. And in this case, it's much easier to evaluate the whatever our intuition says is the same as maximum likelihood estimation. Bartlett considered in 1935 a very special case. Experiment on root starts with the two treatments. Treatment one is, should I sow the seed in season in the spring or in the fall? These are the two seasons. And should I cut it short or long? And then the output is whether it is successful or failure. So such a thing is a 2 by 2 by 2 contingency table. In this, a very brilliant work was done by S.K. Mitra. That was his PhD thesis. S.K. Mitra's PhD thesis was on this Bartlett's model and trying to show some remarkable properties of maximum likelihood estimates. So the response variable is the status, whether it is growing, alive, or dead. Explanatory variables are the season and length of cutting. So when you put these things, then your problem is estimate the expected cell increase under the assumption of no second order interaction. And the model is Pijk is alpha ij, beta jk, gamma ij for all ij and k. And Pijk is a probability for cell increase. and the three-way interaction, etc., assumed to be 0. So the multinomial model gives this, and these are the marginal sums in two-dimensional case. So this is a log linear model problem that fits the framework of theorem 1. Observed data, target marginals, theorem 1 guarantees this. How do I show that? I don't know. So the expected cell counts can be estimated only iteratively to match the two-way marginals. So again, you have to go around and so Dirac and Radcliffe, they studied the same problem with no zero entries, but with positive entries. So our theorem is to also allow zero entries. That's the only difference. And they dealt with information inequality through the information function. And so it is through the information function something was shown. And when this paper was written, too many people were trying to, I don't tell anybody, one of the associate editors, he wanted to join us. That I have also done something, well, let us join together. And then I didn't know what to do. And then I told Bapat, what is this thing? And then he said, no. And then I wrote to Bruvaldi. And then Bruvaldi said, he has no business to do this. I will take care of it. That's all he said. So it was separately published. And then he also doesn't want to hurt the associated because he needs them. Otherwise, they may say, we are not willing to anymore referee papers. So you also need them. So you also write separately something. So this person joined with another person and wrote something. But at the same time, I have to point out, Franklin and I don't know the other name, they also wrote an alternate proof for the same theorem. But Franklin's is to avoid anything to do with topology or anything to do with anything, only based on ordinary differentiation. Okay. But they proved a stronger result than what we did. They showed that this pi is unique. I think it is a very significant proof what they did, those two people. But anyway, there is a whole issue of linear algebra only devoted to scaling problems. Only devoted to scaling problems. But I'm not anymore into any of these things because it's a conference on matrices. That's why I presented this. Otherwise, I could have presented something else in game theory. That's where my heart was. But whatever it is, that's all I want to say.
Thanks very much. We have time for questions or comments. Okay, I'll ask a general question. I mean, one of the nice things I liked your talk was the different ways of scaling a problem can bring advantage. Do you have any idea when it was first used, the notion of scaling to get out of a difficult problem?
No, one of the first one is the scaling for the what do you call Gaussian elimination. That's one thing which was very fruitful use. And then the other one was in the other estimation. In 1961, somebody started. See, after all, almost any mathematical thing, any kind of thing. First, you have the intuition of how this might go, and then only your rigor comes later. So that person came with a brilliant idea, that Friedlander or somebody. and estimating how many people are married, how many are widowed, etc. Well, when the population changes, what will be the change? Many entries were unknown, but still you have a way of estimating them. Yeah, that's. But only thing which I really want to sell is, please be inspired also by a physical problem, and then translate it into a mathematical problem. Then you have a lot to. That means the physical problem itself will push you towards how to mathematize it. Otherwise, you should be a born mathematician like Ramanujan, where everything is mathematically thinking is mechanical for such a person. It may not be for everybody. Even people like von Neumann, many things were only physically motivated. Many things were only physically motivated. So in some sense, it's not a bad idea to somebody wants to talk consultation, I said, fine, take it. And you may suddenly find something out of it. That advantage is there. Yeah.
Wise words.
Okay.
Thank you very much.
Thank you, Professor Iclaa, for chairing this session. We have 5 minutes, then we'll start the next session. We'll be at 3:05. No, tea will be after this session.
Oh, yeah, sure. நல்லா பார்த்துட்டேன் பரவாயில்ல பரவாயில்ல என்ன இதுதான் போயிட்டு யாருக்கும் yeah.
We'll now move to the session of invited talks. Professor R. Balaji will chair this session. Sir.
Welcome to this talk. The speaker will be M. Rajesh Kannan, Department of Mathematics, IIT Hyderabad. So I invite him to give this.
Okay.
Okay. Good afternoon, everybody. Yeah, first of all, I thank the organizers for the invitation and for the nice arrangement. First day event, I was not able to attend in person, but I was seeing in YouTube. So Steve was making a comment. The success of this conference is the beginning. Some of us are like contributed speakers. Now we have upgraded to invited speakers. So I'm one such person. So I came to this conference as a contributed speaker. Now invited. Yeah. Okay, so so title of my talk is Real Infinity Analog of Algebraic Connectivity. This is my joint work with my graduate student, Mr. Rahul Roy. So first, let's start with the basics. So throughout this talk, we'll be working with simple graph, okay, undirected and finite graph. So given such a graph, one can associate various types of matrices, and we can study the structural properties of the graph using the spectrum of the associated matrices. So we will focus on two such matrices now. So first one is the adjacency matrix. So this is an n by n matrix, where n is the number of vertices. So both the rows and columns of this matrix are indexed by the vertices. The ijth entry is 1 when the corresponding the row index and the column index are adjacent, and it is 0 when they are not adjacent. Okay. It's a simple graph. We don't have any loops and all, so diagonals will be always 0. And Laplacian is defined in this way. The Laplacian is the difference of this degree diagonal matrix minus the adjacency matrix. The diagonal degree matrix is a diagonal matrix whose all the diagonal entries are is the degrees of the corresponding vertices. Okay. So it's a simple example. Maybe I can keep this. So the structure, the spectrum of the graph tells a lot of things about the structure of the underlying graph. Just I'll recall quickly a couple of things. If G is a bipartite graph, then the spectrum of the adjacency spectrum of the graph has the spectral symmetry. By spectral symmetry, we mean whenever lambda is an eigenvalue of A of G, then minus lambda is also an eigenvalue of A of G. Okay. In fact, this property characterizes bipartiteness. If you have a graph which has spectral symmetry, then the graph should be a bipartite graph. Okay. And if you assume G is connected, then it's good enough to assume only the spectral radius and the negative of the spectral radius. If both of them are eigenvalues, then the graph is bipartite. Okay. And we can give some bounds for spectral bounds for some of the like hard quantities like chromatic number, clique number, and so on. So this is a classic result by Hoffman and Wilf. The chromatic number is a minimum number of colors required to color the vertices of the graph in such a way that no two adjacent vertices receive the same color. So it's an NP hard quantity. We don't have any easy algorithm to calculate this. Can think of this as a like spectral bound for that quantity. Okay. So the inequality on the right, the chromatic number of G is less than or equal to 1 plus the largest eigenvalue of the adjacency matrix. Lambda 1 stands for the largest eigenvalue. Lambda n stands for the least eigenvalue. Okay. The chromatic number of G less than or equal to 1 plus lambda 1 of G was established by Wilf, and the other side inequality established by Hoffman in 1960s and 70s. Okay, so if you are seeing this for first time, maybe here it looks like chromatic number is an integer where you're giving a bound something like 1 minus something. So adjacency matrix is a trace zero matrix. So if you have an edge in the graph, then lambda 1 is strictly positive. That forces that lambda n should be negative. So you will get 1 plus something. Okay. So, and the second matrix, the Laplacian, so that contains many interesting properties of the graph. So one such thing is the Laplacian is always a positive semi-definite matrix that one can show, and 0 is always an eigenvalue. the second smallest eigenvalue of the Laplacian that tells you whether your graph is connected or not. So precisely it says the second smallest eigenvalue is different from 0 if and only if the graph is connected. Okay, and in fact, this quantity, this second smallest eigenvalue, can be used as a robust version to measure the connectivity. You know about the Cheeger's constant. You can give bounds for the Cheeger's constant in terms of the second smallest eigenvalue and so on. Okay, and you can use this Laplacian to count the number of spanning trees in the graph. Okay, so if you want to calculate the number of spanning trees in a graph, just take any entry from the Laplacian, calculate the cofactor associated with it, that will give you the number of spanning trees in the graph. Okay, so each spectrum has its own disadvantage. The first thing is, if you see the connectedness of the graph, you can't infer from the adjacency spectrum, and the bipartiteness of the graph you can't infer from the Laplacian spectrum. Okay, so yeah. So now let us move on to what I want to present. So the motivation starts from the second smallest eigenvalue. This is also called algebraic connectivity. This term was coined by Fiedler. So it will justify why it's called algebraic connectivity. Okay, so let gamma of g and mu of g, okay, mu of g and mu of g denotes the vertex connectivity and edge connectivity of the graph G. Then Fiedler shown that this a of g is the second smallest eigenvalue of the Laplacian, is less than or equal to the vertex connectivity, which is less than or equal to the edge connectivity. So if you look at this expression here, if algebraic connectivity, if the second smallest eigenvalue is high, that means that your graph is really well connected. So the second smallest eigenvalue give an algebraic way to measure the connectivity. That's one reason he calls that as algebraic connectivity. Okay. Yeah, this we have already mentioned that G is connected if and only if A of G is strictly greater than 0. And the eigenvector corresponding to the eigenvalue A of G is called Fiedler vector. The Fiedler vector found a number of applications in this partition problems in data science. Okay. And so if you use the variational characterization for the second smallest eigenvalue, it has a formula like this. A of G is just minimize the quadratic form X transpose Lx over the unit sphere, subject to the constraint that the vector X is orthogonal to all ones vector. Okay, if we take all ones vector is the eigenvector corresponding to the least eigenvalue 0. So for this, in order to calculate the second smallest eigenvalue, the variational characterization says that just to minimize this quantity X transpose Lx in the subspace perpendicular to the all ones vector. Okay, that's simply we can write the sum of the entries of the vector X should be equal to 0. Okay, and so here like by 2 norm I mean this quantity, the usual Euclidean norm. And it's a standard exercise in spectral graph theory. This X transpose L of G into X you can write down as the sum of squares expression. This X transpose L of G X is equal to this expression which I have written here. So if you take this expression for granted, then positive semi-definiteness of matrix you can see it's apparent. Yeah, so this is the key place. So in 2024, Geerdal and Anted, so they looked at this expression. I think before that some people looked at it, but I started from their paper. So instead of taking this is kind of a 2 norm, and here we are using 2 norm. So if you replace these 2 norms by 1 norm or infinity norm, what will happen? By 1 norm I mean instead of squaring this quantity, just take only absolute value here, and instead of minimizing over the unit ball with respect to 2 norm, focus on the unit ball with respect to 1 norm. Okay, and similarly with respect to the infinity norm we can pose the problem. So you take instead of this quantity maximum of this absolute value of xu minus xv subject to infinity norm is equal to 1. Okay, we can simply generalize these things. Does it have any combinatorial significance? Okay, so we will see those things. Okay, so these notations are standard. Like the L1 norm of a vector x is given by just take the absolute value of all the entries of the vector x and sum them, and then infinity norm is just take the absolute value of all the entries, pick the maximum among them. Okay. So Andrade and Dahl they have proposed this notion. So B of G is like in the previous expression, if you remember, instead of the square and 2 norm, just replace them with the 1 norm, and gamma of G is replaced with the infinity norm. Okay. The optimal solutions for these two optimization problems, B of G and the gamma of G, are called L1 Fiedler vector and L infinity Fiedler vector. And it should be clear that these two quantities are finite and they exist because we are maximizing or we are minimizing a continuous function over a compact set. So this is a meaningful, well-defined quantity. Okay, so let's go to commutative significance. So for a non-empty set, yes, subset of the vertex set, okay, which is a proper subset of V, let's say, the cut induced by the set S is denoted by this dou S. So dou S is set of all edges which are having one end in S and the other end in S complement. Okay, so kind of you're partitioning your vertex set into two parts, S and S complement. Just count. You see the number of you see the crossing edges. Collect all those things. So we are calling that as dou S. So given a cut like this, we can define the concept of the edge density or sparsity, the sparsity of the cut. So that is called a cut. Why it is called a cut? Why it is called a cut? If you cut it, I think the graph will disconnect. So the edge density is defined in this way. Just the number of edges in the the boundary or this dou S divided by cardinality of S into cardinality of S complement. So cardinality of S into cardinality of S complement will give you the number of possible edges between S and S complement, and this, so that justifies the name density like this. So out of which how many of them are really presented in the graph? Okay. So we say a cut is a sparse cut if it minimizes this quantity rho S. Okay. So yes, we are varying over various subsets, all possible subsets of all possible proper subsets of V of G. Okay, so we are going to get some number of quantities for rho S size. So we say a cut is sparse cut if that's the minimum for this quantity. Okay, so Anted and Dahl were able to show that the B of G, the L1 optimization problem which we consider, the optimal value of the problem is equal to the number of vertices by 2, n by 2 into the sparsest cut, value of the sparsest cut, a special type of sparsest cut, where this S we are taking over all non-empty vertex subsets such that both S and S complement induces connected graph, connected subgraphs. Okay, so this appeared in LA in 2024. The bad news is sparsest cut is not an easy problem. That's an NP-hot problem, so we don't have any scope to calculate this B of G efficiently. Okay. But fortunately, the L infinity version, of the problem is not a hard problem. So they were given a linear programming. They have formulated like n linear programming problem. So each of them looks like this. Okay, it's not very hard to formulate. Okay, but I don't want to scare you with all the notations. Okay, so assume that they have proposed a linear programming problem. So basically, n linear programming problem, you have to solve all these things. You pick out the minimum of like all the n optimal values that will give you B of G. So with this reasoning, they have shown that this problem is solvable in polynomial time. Okay, but our question was like, can we do it better? Like, can we give a more? Is there any way to give more combinatorial meaning to this quantity? Yeah, we are able to do that. Just I'll present that what we did. If you have any question, please feel free to stop and ask. So we need some notations. Just I will formalize whatever written there. So let's script F denote the set of all vectors which are having norm 1 with respect to the infinity norm, which are orthogonal to all ones vector. And given a x in that F, you define this function gamma x of G to be take the maximum of the variation of this vector xu xv along the edges. Okay. So in this notation, this gamma of G, that is the optimal value of the L infinity optimization problem, is just nothing but the minimum of this gamma x of G, and x varies over this F. Okay, just we are just reformulating, okay? Rewriting that. Okay, a vector for which this minimum is attained, we call this a L infinity Fiedler vector. Okay, this notation we will use in the proof. That's why I'm again recalling these things. So our first result is. Okay, so we are associating a new quantity, a new numeric with a graph. Okay, so first of all, whether that says anything about the connectedness, we are able to say the connectedness of the graph is revealed by this gamma of G. The proof is not hard to see. So I'll just briefly tell. So if the graph G is disconnected, let us say at least it has two components. And let us say without loss of generality, one of them is having less cardinality. Cardinality of C1 is less than or equal to cardinality of C2. Then define this vector xv in this way. So the xv is equal to 1 when the vertex v is in one of the components, and it's equal to minus of C1 by C2, the cardinalities, if the vertex is in the other component. Okay. So now you can just verify that this vector x defined in this way is orthogonal to all one's vector, and its infinity norm is equal to 1. Okay. So for this vector, like we can calculate this gamma x of g is equal to 0, and since the gamma of g is the minimum over all gamma of x, first for some x it is equal to 0, its gamma of g is equal to 0. So if the graph is disconnected, then gamma of g is equal to 0, and if gamma of g is equal to 0, then you can show that the graph should be a disconnected graph. So how to show? So let's take xb L infinity vector that is gamma x of g is equal to 0. So gamma x of g equal to 0 means, you look at the definition, minimum of absolute values of xu minus xv, where uv is an edge. Okay. So whenever there is an edge between two vertices u and v, the absolute value of xu minus xv is equal to 0. That means xu equal to xv. If the graph is connected, okay, then like we can show that like at every vertex we should have value of this xv is equal to 1. Because between any two edges, if I have an edge, the end vertices of the edge has same value. Okay. Since the graph is connected, I can go a path to any vertex. It is going to say everywhere I should have 1 equal to 1. Okay. But what's the contradiction? But if the all one's vector is not perpendicular to all one's vector itself, hence this so this is the contradiction we are getting. Okay. So if so that forces that gamma of g should be different from 0. Okay. So okay, good. Like we are able to say if the graph is connected, then gamma of g is strictly greater than 0. Okay. Our main aim is to prove to give the combinatorial meaning of it. Okay. So I need some more basic definitions. I'll recall. So distance between two vertices u and v is denoted by d of u comma v. So length of the shortest path between the vertices u and v. And the diameter of the graph is, just take the maximum of all possible distances, call that as diameter. And for a vertex u in v of g, you define SR of u to be the set of all vertices which are at distance r from the vertex u, kind of the sphere centered at u with radius r. Okay. And yeah, so distance matrix, it's an n by n matrix whose rows and columns are indexed by the vertex set of the graph G. The uv entry is the distance between the vertices u and v. So there's a small notation. dm of g denotes the maximum row sum of d of g, and tr of g, that's a transmission of a vertex u. The transmission is for a fixed vertex, you measure the distance from the vertex to all other possible vertices, sum them. Okay, so these things will use. Okay, so first we will look at the vertex transitive graph. So we say graph is vertex transitive if for any pair of vertices there is an automorphism of the graph G such that one vertex maps to the other one. Okay, for any two pairs it will. The first basic result is if G is a vertex transitive and a connected graph on n vertices, then for every u in the vertex set of G, we have this formula. This optimum value is nothing but n by the transmission of the vertex u. I feel this is an elegant formula. Instead of solving this LPP like directly, you can calculate this transmission of u can be calculated efficiently in polynomial time. You can use the BFS algo to calculate. Okay. So the proof goes like this. So for every vertex u in V of G, okay, if you consider the number of vertices in the sphere centered at u with the radius r is ai. Okay, this quantity is same for every vertex since the graph is vertex transitive. So this is independent of the vertex. Okay. So that says that the transmission of the vertex u, like that is the sum of the distances from the vertex u to remaining vertices, I can write down in this neat way. So what is the expression? So this is r equal to 1 into a1, that is 1 into the number of vertices which are sitting at distance 1, and so on, 2 into a2 and so on. Okay. So let us give a name to this quantity alpha, n by a, this transmission of u equal to alpha. proof by contradiction. Suppose let us say I can find out a vector x for which this gamma x is strictly less than alpha, then I'm going to get a contradiction. Okay, the contradiction, so how to proceed? So let me take a vertex v such that xv is equal to 1. Okay, x is part of in script f. Okay, so it may happen that x does not contain 1. If it is the case, you work with minus x. Okay, you will get the same quantity. So xv equal to minus 1, xv equal to 1. Okay. Then if you take any vector x vr, which is any vertex vr, which is in the sphere of radius r, then one can easily see that the xv rth component of the vector x is strictly greater than 1 minus r alpha for every r lying in between 1 and d. Okay, for r equal to 1, you do like you will get that how to extend for general number. Okay. Just we need some calculations. And so just you calculate this xv xu. So we will be showing that the whatever calculation or computation we have done, that's going to tell us the sum of these xu's is strictly greater than 0. But we have taken x in script f. So the property of vectors in script f is this is orthogonal to all one's vector. That is, sum should be equal to 0. But here I'm getting a contradiction. The contradiction to what we have taken here, gamma x of g is strictly less than alpha. That's not possible. So it says that gamma x of g is greater than or equal to alpha. What about the equality? So we were able to construct a vector in script f for which equality holds true. That completes the proof. Okay, so for the vertex transitive graphs, this is the proof. And using this, we were able to give a proof for arbitrary graphs. So the idea, so if G is any arbitrary connected graph on n vertices, then this gamma of G is n by maximum of this transmission. Okay, the argument is just look at the orbit partition. Take a vertex, see its part orbit, okay, and then on each of the orbits you calculate this n by transmission of u. Using that we can.
Can you do it by induction?
Sir?
Induction on n.
He is asking whether you can do it by induction or not.
Understood. Thank you. Our proof is like it relies on the proof for the vertex transitive graphs, which we did earlier. So if your question is, can you do that in induction? I don't know. We were able to prove by contradiction. Induction proof, I didn't think of. Maybe I'll think about it. Thanks. Okay. So again, so this shows that if even for arbitrary graph, like we have a nice formula for this gamma of g. Okay. And just we are thinking, suppose if you are working with a tree, what will happen? If you are working with a tree, like problem is much more simpler. You don't have to like look at the transmission of all the vertices. Just look at the transmission of the only the pendant vertices. That's going to tell you the maximum of only the pendant vertices you look at. That will give you the formula for it. Okay. Okay. So when we are writing paper, you are giving, because when we read the LA paper, even calculating this B of G for each family subgraphs, it's a really difficult. They have done a lot of calculations. By this nice formula, like in one shot, like we can calculate everything. Reduces to calculating just the transmission of the vertices. Can calculate. Okay, so one more thing is in the PN, this formula is given in the Anted and Girdhal's paper. Rest of them like we have. Okay, so now I have a nice formula. So we have a graph, we know how to calculate it. On a graph, we can perform some operations. Okay, just we started with take the Cartesian product. So if you take the Cartesian product of graph, can you give a nice formula for this gamma of the Cartesian product in terms of its constituents? In general, we may not get a nice formula. So fortunately, we got this nice expression. So the Cartesian product of two graphs G and H. Its vertex set is just the Cartesian product of the vertex set of the graphs G and H. Okay, so two vertices u1 v1, u2 v2, they are adjacent. If and only if either the first components u1 is adjacent to u2 and v1 is equal to v2, or u1 should be equal to u2 and v1 is adjacent to v2. Okay, so this is the way we are defining the Cartesian product of two graphs. And it can be extended for n number of graphs. Okay, so if you consider the Cartesian product of n graphs, then this gamma of g, gamma of this products is given by this some sort of harmonic mean. Okay, So when you are doing these things, like natural thing is like we have started thinking about how to calculate gamma of g of cube graph. So we are able to get some nice formula for general product. So as a consequence, for cube and Hamming, for those families, we got some nice formula. Okay, and then can we connect with some spectral quantities we were trying? We were able to connect with the spectral radius of the distance matrix. So this bound is if gamma of g, if for any connected graph on n vertices, this gamma of g is less than or equal to n by the largest spectral radius, and we are able to show that the equality holds if and only if the graph is a transmission regular graph. Yeah, so B of G is the quantity which is NP hard to calculate. So can we give some nice bound for B of G in terms of gamma of G we were working? So we are able to show that B of G is at most m by 2. M stands for the number of edges, m by 2 into gamma of G. So just a comparison, like the first two columns were given by Anted and in Dahl's paper. Just I appended the third column. So one of the motivation to consider this L1, the problem with respect to L1 norm is there's something called L2 graph smoothing. Okay, so in algebraic connectivity, if you see this expression, the sum of squares expression, so it says that you are taking a vector and you are measuring the difference of the components of the vector with respect to the edges. Okay, in L2 norm you are seeing. Okay, so how smooth the so that's the reason some authors call this as an L2 graph smoothing problem. So if you just like we can take the terminology from there. So L1 graph smoothing is like instead of 2 norm you do it with the 1 norm. And similarly L infinity we can do. Okay, the solution just we have given name. So whether it encodes whether this optimal value of this optimization problem, whether they encodes the connectedness in all three cases, that's the thing. And what is the commutatorial significance or relevance? So L2 smoothing, it's useful in partition. So here in L1, they were able to explicitly show that this is connected to sparse cut. We are able to show that L infinity, this optimal value is the max, it's related to the max transmission. Okay. And the strategy to calculate those things, here it is spectral. And then for L1 graph smoothing, it's an NP-hard problem. So here it is polynomial time, and we are able to give an explicit formula for it. Okay. I think I will little fast. Okay. So these are all my references. I just given only the important references. So this is the paper we started with, combinatorial Fiedler theory and the graph partition by Anted and Dahl. And this is the paper by Fiedler where this notion of algebraic connectivity introduced. And if you want to see something about the sparse cut and the graph partitioning applications, this is an very interesting lecture notes. If you want to know what is happening, how to apply spectral graph theoretic methods in theoretical computer science, it's a nice place. And Poem wrote a fantastic survey article. It is available in his web page. You can go through over it also. Okay, that's all for the day.
Any questions?
Yes.
Can you also relate the gamma of G with A of B?
Yes, we have that. Yes. Bounds for the yes, sir.
Upper bound for the upper bound. You know, you're given the relationship, going the other way around between these two new quantities.
Yes, sir. Both upper and bound we can use. But the problem is we don't know how sharp it is, and we can't expect the sharpness because one is a NP-hard quantity, another one is a polynomial type quantity.
Any other question? Okay, if there is no other question, please give a hand to the speaker. Thank you very much. Thank you. Next speaker, Dr. Jam Prasad. He comes from MIT Mahe Manipal. I think this institute. Okay, so he comes from Manipal University. Where is he? Oh, okay. Sorry. Welcome. Please go ahead. Okay, sorry. He asked me to wait for some 2 or 3 minutes, have a break because
3:45.
That's what I did. I'm not getting it. So, yeah. Coding no deep knowledge in this is quite a yeah, clear cut enough problem. Sure. It is very full. So this is actually helping them. Okay.
So this is not.
Yeah.
Can I
they are able to map immediately. No, but if you make it opposite related to original way, you are doing so many other things. Of this.
This has okay. So I have to find some.
Suppose you make that one. Yeah, you can, but if you say at least, instead of this matrix, you are taking CW.
Yes.
Yeah. Provided this matrix has the W, has the zero pattern.
with 0%, we do not know about it. That is the, yeah. So what is the 0%? That means every non-zero entry must be on a positive diagonal. This is the theory. Given the issue testing, it's a convex combination of allocation rate. Yes, yes, yes. I get that, yeah. So, we will really hard time. In fact, when Robert was to school, and I was trying to tell him, this is the theorem. But he says it's not only theorem, but it's really a concept to do it. So what he said was, yes, sir. So 307. That's a very normal. So this is the matrix. So all he's saying is, you start with any entry, then there should be a diagonal through this one, which is possible. All the entries are possible. So, for example, this.
The diagonals of this and this.
No, that by diagonal I mean, this is the only entry in the row and column. This is the only entry in this row and column. This is the only entry in the row and column. Then it's called a diagonal.
Okay.
That's what it is.
Each row and column, you have to single.
Single.
Yes.
And yet it should cover all the columns. Then it's called a diagonal.
Like pseudo.
Yeah. So now, certainly I can write this as a.
But by there are two.
Point two, so we write down 0.2, 0.2 plus whatever is the difference. That difference will be 0.4, here it will become 0. One more 0 will be introduced. Each time a new 0 is introduced, you have fewer diagonals. So like that you can do, and then you can finish everything. Okay, that is the idea. And then it requires the 0 factor. For example, just to give an example.
Also like this.
That's what was it?
Hello. Chale.
Yes, sir.
Okay, Dr. Shyam Prasad is a professor and head of Department of Mathematics at MIT. He is a guide for several PhD students. He does research in algebra, fuzzy set theory, rough set theory, and graph theory. He is a university first rank holder in MSc, UGC project fellowship he has, CSIR, SRF also he has cleared. IMS prize for best paper in algebra in the year 2000. INSA exchange programs also he has done. And he has authored 2 books. One book named Discrete Mathematics and Graph Theory, Nearings, Fuzzy Ideals and Graph Theory. That is the second book. And one more book also he has written, Nearings, Near Fields and Related Topics, published by World Scientific in the year 2017. He holds a life memberships in Ramanujan Mathematical Society, Indian Mathematical Society, and others. So this is the citation for the speaker. And also I forgot to tell about Rajesh Kannan. Rajesh Kannan, so just about 1 minute, he's an assistant professor in Department of Mathematics at IIT Hyderabad, the previous speaker. His research focuses on algebraic and spectral graph theory, matrix theory, and also combinatorics. He has published more than 25 research articles in linear algebra, combinatorics, and graph theory. He has received the Excellent Young Teacher Award in the year 2020. He had a postdoctoral fellowship at the University of Manitoba in Canada in the year 2015. German Israeli Foundation postdoctoral fellowship in 2014, and also Indian Statistical Institute visiting scientist fellowship in 2013. So that was a citation for Dr. Rajesh Kannan. Now let me welcome Dr. Prasad for to give his talk. Thank you.
Thank you very much, sir, for introduction. So actually, my field of research is not much aligned with this theme of the conference, but still, thanks for the organizers for giving me an opportunity. I'm an inside department faculty, as you know, but due to some other overlap works, I could not attend the sessions this time. I'm sorry for that, but now title of my talk is Small Ideals of N Groups and Related Graph Theoretical Properties. My broad field of research is near rings, which is generalized rings, and also sometimes we connect with the graph properties, not much deep into the graph property, but in a very peripheral level, and then some links to ideal theory, ideals, how these ideals in N groups or the near rings, and how we can connect to some algebraic properties of graphs. So it's not deep results, and the content is very simple. And this is what the work is not very new, but it published last 2 years in some good moderate journals. So combination of my co-scholars, other scholars, and students. Okay, thank you. The contents of my presentation goes in this way: module over engineering, essential ideal of an N group, essential ideal graph of an N group, small ideal graph of an N group, and generalized essential ideal graph, matrix nearing, and there are some recent references. This includes. So as you know, this ring is associative ring, but now the new structure is a nearing is a classical generalization of a ring, where all the axioms of ring holds, but except two conditions. One is not necessarily abelian, and only one distributive law is taken into account. But normally, the researchers consider the only right distributivity, but some of them use left distributivity, but exactly one holds. So naturally, every ring is a near ring, but the converse is not true. So it's natural example of a near ring. You take any group, not necessarily abelian, and take the maps from G to Z. And with respect to pointwise addition of mappings and composition of mappings, this becomes a right near ring, but not a ring. So here the operations are pointwise addition and the substitution of maps. And also take a vector space for a field and find maps you consider maps from V to V, Mx plus C, where X and C are V and M is from here. This is also near ring, but not a ring. And in case of rings, we have many axioms or two properties, fundamental properties, where you take n into 0 is 0 always, and 0n is also 0. This allows there because of both the distributive properties. But in case of near ring, only one is allowed. 0n is 0 because I am considering only right near rings. And n0 is not equal to 0, not allowed. That means there exists at least one element wherein this condition fails. Now, if you look at one set such that where these two are coincident, n0, all elements of n wherein n0 equal to 0, and I'll call this as the zero symmetric part of n. At the same time, if this coincides with the entire nearing n, then we call it as a zero symmetric nearing. Otherwise, it is a subset, and some additional property will be a sub nearing also. And nc stands for all elements in n where n0 equal to n. This is the constant part of n. And if this coincides with the entire n, then we call it the constant nearing. and the intersection contains a zero element. Then the Pierce decomposition, we call it as n decomposed as two sets here. One is the n naught, the zero symmetric part, and then is the constant part of that. And this is the best example for zero symmetric nearing and the constant nearing, and also just a nearing. All zero equal to zero, you take any group, additive group, and mg stand for nearing. And all maps from G to G has that f0 equal to 0, and the next one f is constant, and the third one is the nearing. First one is the zero symmetric, second one is constant, other one is just nearing. Like in a vector space for a field and module over a ring is well known to all of you. Module over an associated ring, but if I consider module over a near ring, because near only have one distributive property and not necessarily abelian with respect to plus, and you have a map from n cross G to Z, and action of group over n left side from left side, and the properties n plus n dash G is ng plus n dash G, and compatibility n dash G is n dash G is the action, and every nearing act on itself trivially, and also take any group Z and over Z, and this becomes an Mg group. And like in rings, we have left ideals, right ideals. In case of non-commutative rings, in case of commutative rings, all are same. Non-commutative rings, we have two-side ideals also. But in case of near rings, we have ideals and n subgroups. We can say that this subgroup is an ideal provided n subgroup, sorry, n into delta is contained in delta, and a normal subgroup you take of Z, delta of Z, then n into G plus delta minus ng belongs to delta. In that case, we call it as an ideal of an n group. Because this n into G plus delta minus ng is based on the quotient has to give you the n group, whole n groups. Suitably, we have defined this ideal. And coming to the essential ideals, if you look at a vector spaces or a field, either it is a maximum linearly independent set or minimum set which spans the space. But when it comes to module over rings, these are different. These two are different. One gives you in terms of essential ideals leading to Goldie dimension. Other one is the spanning dimension. If you take a spanning elements, so very similar to the module over rings, we have an n group. One is the essential ideal. Another one is the either small ideal or superfluous ideals. So what do you mean by this essential ideal? You take any ideal of I of an n group Z. If it meets with 0, then this has to be 0, J has to be 0. So that means if the intersect, any non-zero ideal you take, then the intersection always non-zero, I intersection J. And G is uniform provided if every ideal satisfies this property. And complement means that an ideal J of Z is said to be a complement provided this J is the maximal with respect to intersection 0. That means any ideal K with I intersection K non-zero, and K is an ideal G which contains I. So that means J itself is the maximal. Now coming to graph, we were defined on these essential ideals. Essential ideal graph is denoted as EC, is a graph whose vertex is the non-zero proper ideals of Z, and take an edge Ig provided I not equal to Z, and we have avoided the self loops because graphs considered as simple and finite, and the sum is essential ideal. In that case, we take the edge Ij, and this has some properties connecting to underlying algebraic structure nearing. So there are the simple examples here. And Z2 cube you take and form a group Z2 cube with a addition table from Sonata. One of the software, it gives you less than 32 size of the nearing order, and take the multiplication in this way. So then these are the ideals, and the corresponding graph is this, because I take the only essential ideal. If the sum is an idea, sum is essential, then we draw an edge. Otherwise, there is no edge. And if Z is finitely generated, this finitely generated means set of elements which generates complete G in group G with zero symmetric. That means you are considering n coincides with n naught, then every proper ideal of G is contained in a maximal ideal. This is already existing. And if n equal to n naught and G is finitely generated containing a unique non-zero maximal ideal, say M, then it becomes adjacent to every other vertex, because it becomes a universal vertex in EG. And simple other one is that A belongs to vertex set of G with a universal vertex. If A is not essential in G, then A is a minimal ideal of G, and moreover, if A is a direct summand of G, then A is simple. There are some properties which on this. And you take any essential ideal, then you add one more ideal to that, always essential. That is bigger than the essential, always this intersect with any other non-zero ideal. So this is a trivial property, and any proper essential ideal of G is always an universal vertex in the essential graph of G. And take an ideal, I dash be its complement, then always the sum is essential. And take a zero symmetric nearing, and G be finitely generated as an N group, then every non-essential ideal of G is adjacent to its complement in the essential ideal of G. And that's connecting to the diameter, because once you have studied the graph properties, we'll see that connectivity and the diameter and maximum connected diameter bounds for diameter, these are the common properties we look at. And in case of these essential ideals also, if you look at geosymmetric, if you consider and finitely generated as an ideal N group, finitely generated N group, then this EG is a connected graph with diameter at most 3. And there is proof, but I'm not going to details. And proper essential ideal graph PG denoted as PG, and is a subgraph of the essential graph induced by the vertices which are non-essential ideals of G. And there are some properties of this proper essential ideal graph. And if n equal to n naught and G is completely reducible, that means sum of all simple ideals. Completely reducible means it is sum of all simple ideals, or every ideal is a direct summand. So that means there is an I is a direct summand, means that there is an ideal J such that I plus J equal to complete G and the intersection is 0. So in that case, the following three are equivalent. If the G is not simple and G is completely reducible, and this graph is same as the essential ideal graph, and there exists a vertex with degree of x is in EG is same as degree of x in PG. So there are, of course, this is the consequence of that. It's not that. And the dual of this essential ideal is the small ideal or the superfluous ideal. So here we consider the sum instead of intersection meeting 0 and the ideal becomes 0, but you take the sum here. G is an N group, and ideal S of G is said to be small, provided the sum is G and K is an ideal of G, implies that this K is G. So in that case, we say that S is a small ideal, and G is hollow, provided every proper ideal is small in G. And because of nearing need not be computed any time, therefore we taken some examples which contain some matrices. And G act on G stands for N itself, because N act on itself again. And so because the notion complement is, you have this, and supplement is very similar to complement. It's a dual notion. Suppose H and K are two N subgroups, and the K is said to be a supplement, provided H plus K is Z, and H plus K dash is not equal to G for any proper ideal K dash of K. And there are some examples on this. And what about a graph connection to these small ideals or superfluous ideals? So now construct a graph here. Small ideal graph of G is denoted by SG, and the graph having the set of non-zero proper ideals of G as vertices, and two vertices I and J are adjacent, provided their intersection is small in N. Is the symbol is for small. Sorry, here small in G is not N, because N group I am taking module over N. Right? And there are if G is a simple, then the corresponding graph is a null graph. And suppose G is a local N group with non-zero identity which contains only one maximal ideal, then every proper ideal of N is small. In that case, it is a complete. And take a polynomials, quadratic polynomials over Z2, coefficient from Z2, and a G is same as N itself. And we have ideals here, non-trivial ideals listed here. The ideal T square plus T is generated by T square plus T is small here, and the corresponding graph is this. And similarly, some computations with the examples. It is making use of the Sonata here. And another property is every non-zero small ideal of G is a universal vertex in the graph constructed over the small ideal graph. That means adjacent to every vertex in this, every non-zero small ideal. And the graph for SG minimum of G induced by minimal ideals of G becomes a clique, is a complete subgraph of the SG. And there are some other properties connecting to annihilators. And when you take any ideal I of G, the dual annihilator of I denoted by annihilator Di is the intersection of ideals such that I plus J equal to Z. And the diagonal group you take and G is same as N, and you have the computations. If you take any ideal I of G, then I intersected with the annihilator is always small in G. And I supplement is very similar to the earlier, therefore I don't want to give much details on this.
So you agree the proofs?
Yes, no proofs. I'll make you comfortable, sir. No problem. And if you have a DCC, means a descending chain condition on ideals, then every proper non-small ideal of G is adjacent to its I complement in SG. So if you have DCCI, then SG is connected graph with diameter less than 4, that is 3 is also allowed here. And there are theoretical proofs. If anyone want the recent papers, you can check it. And proper small ideal graph PG of G is a subgraph of the superfluous graph induced by the vertices which are non-small ideals of G. But here computation is for small ideals. Okay, there are some, these are not too deep properties, but very simple. Next, take a zero symmetric nearing and completely reducible if and only if each ideal is a direct sum and is known, already stated. And in case of small ideals also, these condition, 3 equivalent conditions hold here. In case of essential ideals holds, but in case of this small ideals also, these 3 equivalent conditions. Completely reducible and the graphs coincides, and there is a vertex satisfying the property. Okay, this is also G essential ideal graph of an N group, and here only the condition is this an ideal I of set to be G essential, provided the intersection 0 and the ideal you have taken is a small in G, but in the essential graph it is just an ideal, but whereas here it has to be a small ideal, that implies that J equal to 0. So in this case also we define a graph provided 2 vertices are adjacent. In that case A plus B is G essential in the whole N group. So there are a similar computation, but computation is for G essential ideals. And this is one, G has DCC and contains only one minimal ideal, then G essential ideal graph is complete. And the other 2 conditions, it's not equivalent, but all are independent. And G is completely reducible, is the N group, then intersection of full magnitude is 0. Okay, these are some properties on complement, G complements and G complement graph, etc. Okay, but whatever the results are true for essential ideals, but it is true for G essential ideals, except 1 or 2. But only thing is here their diameter of this LG is 2 maximum is 2. That means less than 3. But whereas there 3 is also allowed. That is the only difference here. So there is a path between any 2 small ideals in the non-superfluous graph or non-small graph. And the last part of this content is matrix near rings. In case of rings, you know the matrix ring system of all set of all arrays. But in case of matrix near rings, we cannot find the matrix arrays, but we see it as maps. So from R power n to R power n, if R is a near ring. When n is a near ring, then n power n to n power n is maps, set of all n tuples maps. So take a zero symmetric near ring n with 1, and n power n stands for the direct sum of n copies of additive group n plus. And we have a combination of 3 maps. One is the injective map, one is the projective map, and one is the inclusion map. So the ith injective is going to I at A equal to A in ith place and 0 elsewhere. And the projective map is AJ going to Z projection. And one is inclusion map FA from n to n by FA at x equal to ax is inclusion map. You take the composition of all three I for the pi j, then this becomes you can denote it as Fi j power r. Now we take a nearing n cross n matrices over n denoted by mn is defined to be the sub-nearing of maps from n power n to n power n generated by all these maps. So we can't find the arrays directly in case of matrix nearings. It is identified as a set of maps. Now there are beautiful analogies, like you take an ideal in nearing, but what is the corresponding ideal in matrix nearing? And conversely, you have a matrix nearing ideal, but how you bring back to an ideal in a base nearing? So there are certain properties. For that we need some notions. I is suppose you take an L subset of n, then Ln denotes the Cartesian product of n copies of L, and I is take an ideal of matrix nearing. Then how you bring back to an ideal of n? This is I lower star. All x in n such that x is in the image of pi j a, where a is a map from n power n to n power n. So in this way, you can associate ideals of n and ideals of the matrix nearing, whose base elements are n. And similarly, you take a modulo over a matrix nearing, means it is mapping from mn to mn cross n power n to n power n, where a row goes to the map. And if you take L is an ideal, then L power n is an ideal of the modulo or matrix nearing. And here A star star gives you an ideal in n if you take an ideal in the matrix nearing or modulo over a matrix nearing. So these are some equivalences. Okay, this result A power n ideal of this, then both are equal, then A is an ideal n over n, then A power n is an ideal in the corresponding, and other results. Of course, I have not put here many examples because of content. And these are some, suppose you take a small ideal in a similar way. And now this lemma stores, for example, B is a small ideal of n group over n, then B power n will be small ideal in the corresponding module over a matrix nearing. And similarly, take a small ideal in a matrix nearing n power n or matrix nearing mn. Then a lower star star will be a small ideal in n over n. So that we'll get the correspondence between the small ideals of n over n and the corresponding those ideals of mn group n power n. So these are some differences. So majority papers, these are the papers report majority, and the base book for this is GIF engineerings and Theory applications. And these are recent papers, one or two from this literature has taken time. Yeah. Thank you.
Yeah. Any questions from the audience?
Yes.
Or like related to this theory, I've only heard of reduced power graphs, and this is new to me. So is there any relation between reduced power graphs and what you are defined for nearings?
Relation between?
Reduced power graphs.
Reduced power graph, I'm not aware of that first one.
Okay.
Frankly speaking.
Okay.
Yeah, you tell me, then I'll find out if I know that.
I also don't know much because.
Okay, reduced power graph.
I think they are the graphs generated by element powers in the groups.
Okay. I'm not fully aware of that, frankly speaking. I see. Thank you.
Any other question? Okay, please thank the speaker for his excellent talk. We'll go for a.
Thank you, sir.
Is there?
Thank you.
Okay, so we'll go for a tea.
Thank you, Balaji sir, for chairing the session. So tea is arranged floor below, and we'll meet for contributory talk at 4:35 in academic block 3 in first and second floor. Thank you all.
Maybe that may be related to the empowerment.
So because it is defined in groups and then for four different structures, we are defining two different tables. Can you tell?
But precisely.
The adjacency relation is defined as the program of the is part of the project. And there will be
Generator.
So here you power
Yeah,
on the
because if the finally generated, probably faster.
yeah. Like that.
Mostly, because we take finally generated and group by default, the reason we don't, we need multiply. Yeah. So therefore we took those ideas. So probably you can use use of generators like in paragraph in generators. This also mostly one element is the power of something, right? Maybe what properties. You are given any papers and power graph already? Also, because I have not seen it, others is to tell sometimes.
Reduce graph just like to remove the identity.
Call it as reduce, why that?
Yeah, if we remove the identity element and all the elements will stay. Because identity element is adjacent to every other element, so it becomes trivial.
So. We can discuss it. Yes, sir, yes, sir.
Krishna sir was talking.
Yes, yes, sir, yes, sir.
Our is, we met in Bangalore
Yes, sir,
actually,
yes, sir.
2013. NIT. I was in NIT Warangal at that time. I moved to Andhra. Tadipalli. Move అయ్యింది. ఇప్పుడు మీరు చెప్పారు కదా నియర్ రింగ్స్ అని అలా నియర్ ఫీల్డ్ గురించి కూడా మనకి